Hello. Good morning, everyone. So, is my voice audible? Can anybody respond whether my voice is audible or not? Unmute yourself and you may respond.
Hello, good morning, sir. Yes, your voice is audible.
Good morning, ma'am. Thank you. Thank you so much.
Good morning to everybody. Those who can come to Dean PGS, that will be wonderful because our Swiss professor will join sharp at 10:30 from Switzerland online. So I request also the DR to come to Dean PGS. Teachers are coming. We will start soon. Thank you so much. Hello, are you able to hear me? Can any of the participants just revert back telling me that is my voice audible?
Yes, Rinku, it's audible.
Okay, fine. And those who would come here would be getting the certificate. So you can also join at the Dean PGS conference hall. Thank you. And there's also lunch in the afternoon at, Farmers Training Center. Thank you.
Okay, Rinku.
Hello. Can anybody speak? I mean, we just want to test the speaker here in the hall. So you can speak. Anybody? No, I'm sorry. Wait. Hello. Can anybody speak? I mean, to test the speaker here.
Hello? Hello?
Yes, ma'am. You are
Hello?
audible. You are audible. Thank you. Thank
Yeah,
you.
it's audible now? Okay, thank you.
Yeah.
Can we start now? A very good morning to everybody. We are going to start the session today, and the training program is just on a very short notice. We were able to, tell you, and most of you all have gathered. So I just thank you once again. And the training program is on biochar production and its use in agriculture. So we'll be having our speaker who will join us sharp at 10:30 from Switzerland, Professor Jean Bernard, who's a specialist in pyrolysis. So we'll have a 1 hour talk from Professor Jean Bernard. He's already there. So you can, we'll have 10:30, Professor Jean Bernard will be starting. So we'll just join in a minute. Good morning, Professor Jean Bernard. Would you like to share your presentation or shall I share it from here? Am I audible to you?
Good morning, Rinku. Can you hear me well?
Yes, you're very audible and very clear. Thank you so much.
That's fine. I'm doing a few adjustments to make sure
Okay.
I can see at the same time what I
I
present.
I can
So it's
also
okay.
share your slides. I have a
No,
copy
I
of
will
your
share.
slides.
I will share my own slide because they are on PowerPoint, and it's better.
Okay,
But I will
fine.
do that.
Done. Thank you
Okay.
so much. In the meantime, I'll just give an introduction of the program and then at
Yes.
10:30 you will start.
Okay. Okay,
Okay,
that's
thank you.
fine.
Yes,
Yeah.
thank you, Professor. Thank you so much. Okay, once again, good morning to one and all. I welcome you to the training program on biochar production and its use in agriculture. Today we know that biochar and is a very important topic. Why? Because we are facing severe climate change impacts not only in India, all over the world. And for this reason, the whole community, the people all around the world, and the scientists and the others are looking into various ways, means, techniques, technologies to combat climate change. And the three important technologies which would help in mitigation of climate is the first one is what we don't do in India is carbon storage and capture, which I'll be talking to you later. The second is biochar production because it sequesters carbon sequestration by biochar technique. And the third one is grow more trees, afforestation, reforestation, planting. So these are the three ways in which you can do. And of course, we are also doing with the renewable energy, okay? Solar energy, wind energy, various types of renewable energies are also available. Now, as an agricultural college, agricultural scientists, agricultural faculty members, and students of the university, and young entrepreneurs, our job becomes very important here because we play a very important role in helping our climate. And how would we do that? Because organic farming with biochar application or natural farming with biochar application goes a very, very important hand in the coming years because biochar stays in the soil for many years. And that would be appropriate if I would say that a biochar prepared above 500 degrees Celsius would stay for a longer period of time in the soil than a biochar prepared at 300 degrees or 250 degrees. Okay, we come to that later. Anyway, I would like to, with these two, three important points, I would like to say that these are very important things which we have to address. Our scientists are already working and having these climate change impact issues in the forefront. When we think and perform our agriculture in the same way, then we are preventing the climate change to some extent, at least, because we see today as there are a lot of wars and fights happening. We have issues with petroleum, we have issues with diesel, kerosene, and all these things. Even we cylinder is also a problem at the moment. We know, we are hearing. So at this time, how are we going to manage all these issues is a big question. So it will only happen if we all come together and work together in bringing this technology, which is already there. We only have to use it. We have to make an awareness to the farmers, use it and do it on a day-to-day basis. And surely, I'm sure if everyone has a step put forth in the coming days, we will at least manage our carbon dioxide, the greenhouse gas, which is, they're already at very high concentration in the environment. Okay, with these few words, I will just now quickly like to give an introduction to Professor Jean Bernard. So, a quick introduction. Professor Jean Bernard Michael holds a PhD in energy technologies from the University of Valenciennes, France, in the year 1983. And he currently acts as an advisory board member for Race for Water Foundation and as a consultant and trainer. So, from 2004 to 2018, he was a professor at the University of Applied Sciences and Arts, Western Switzerland, where he initiated and led several R&D projects in the field of energy and environment, particularly biomass and waste recovery. He is a trainer for Portugal and has also worked as a consultant and a trainer in Morocco, India, China as well on various occasions. He has gained extensive experience of energy processes and R&D at several internationally renowned laboratories of the Netherlands and the Switzerland, that is IFRF and Batley CSEM. He advises several companies on waste to energy recovery and new energy technologies and continues to train engineers and specialists in renewable energies, bioenergy, and waste recycling. He is also a part of the Solar Impulse expert for the World Alliance for Efficient Solutions, founder of the Swiss Association for Project Management, and a member of the advisory committee www.projectmanagement.ch, that is Switzerland, IPMA Level B Certified Project Management 2001 to 2020. So I know Professor Jean Bernard from 2010, and our connection was from the Swiss Next India. So I had also been to his laboratory in near Fribourg in Yverdon, and I was there for a month. This was in the year 2013. That's how I've seen his very big energy laboratory. I've also visited his, please, sir, also. I've also visited his, pyrolytic units in different parts of Switzerland and seen some of his works. And he's a very knowledgeable and a very friendly professor, very helpful. And he's also helping us here for the energy efficiency of our pyrolytic unit, which we are having at GKVK. So today I'm very much fortunate that Professor Jean Bernard is with us, joining us over here. And Professor Jean Bernard, today we are also having, faculty members who are there in the seminar hall of the Dean PGS, and some of them have joined online. So here we are having about 20 of us at the moment. Some more are yet to join, and we are all here to listen to you. You can take as much as time you have. You can take even 1.5 hours, because I know you're giving this presentation from Switzerland via Zoom. So thank you so much. And if you are ready, we start, or otherwise I wait for 10:30 and I can even engage our participants on other matter.
It's okay, Rinku. Thank you very much for this very nice introduction and your presentation about Biochar. Indeed, it's a long story between us and between me and India, and I really like to come every year. I would like to come more often, in fact. And despite the short notice, I was able to prepare something to show to everybody here. I'm sure there are a few people that are even more expert than me on pyrolysis, but this will give the opportunity to exchange. So, if it's okay, I will start with my video presentation. I will share my slide. So that's it.
Yeah, Professor JB, first we wanted all the participants to see you. So we are trying to just, take away
they
our
see me now?
slides.
Yeah.
Yeah, no, we are not able to see you. We just want to remove our slides. So just a minute, we'll just
okay.
Stop slide share. Yeah.
Okay. When I now you can see me online. Yes, I can share my screen. I see that you can see me. Is that correct?
Because we are not able to become Manu.
No, there are two screens. One for me because I am connected also with my phone, but you should be able to see me because now I have joined the meeting and I see myself also.
We just want to remove this one so that it can be visible to everybody.
Just laptop output full screen give it.
Can you do it?
Yes. Just a minute.
Just showing only one window.
Because we are seeing only one.
So don't, okay. Zoom, if you can click, so you can do that stop share. Okay.
Just let me know when it's okay when I can share.
Yes.
And sometimes the sound, your voice is faint, and sometimes it's high. It's fluctuating. But
Okay, I think then
probably
I will stand very close to the laptop. That is better. Okay.
can't hear you.
Can you share your slides?
I can share now. Yes, okay. I will try. Okay, now. Oh, it's not the one. It's not the one I wanted to share. I will share another one. One moment.
Manu knows. Yes, now we can see you. Okay.
Yes.
Okay, fine.
And why can't I share my screen? It doesn't work.
Yeah, can you please get into full screen? Yeah.
I'll share again. Now, one moment.
Yeah,
Okay.
that's fine.
Now. It's coming. Yes.
I can get into
You
full
can-
screen, sir.
Yes,
Can you
I will do it on full screen now. Yes.
Yes, thank you.
Which give you back, sir? Which give you the back?
Huh.
And you give
Yes,
your
sir.
name for
Yeah.
certificate.
Yeah, I will.
Why is not coming? 5. Well, okay. Fine.
Yeah, it's
Everything
fine.
okay? Okay,
Yes.
good.
Thank you, Professor. Go ahead.
Okay, 1 moment. So, good morning to all of you. I don't know how many you are, but I hope you can hear me well.
Yes, yes. Everyone can hear you. You can all
Yeah.
say hi. So they're all wishing you
Hi.
hi. They're wishing you
Hi.
hello.
Hi.
Hi.
Nice to see you, everybody. So it was a short notice, but hopefully I had some material which I gathered together. I will mainly speak about pyrolysis, some words about, of course, about biochar, but you probably know already quite a lot about that. And from the program, I saw that there was a previous speaker. Am I right, Rinku? There was.
No, Professor, you are the first speaker. You are the first speaker.
Okay. Because
Yes.
I presented in a way that I would follow the other professors. But anyway, no problem. Uh, if you have any questions, you can keep them for after the presentation or interrupt if it is really if you need to. No problem for me. So pyrolysis, and it's important to climate change. Now, first of all, you probably know the situation. Just to recall it, the consumption today has raised, no, it's not right, it has raised to nearly 16 gigatons of oil equivalent. I still speak in oil equivalent, although IEA, now they work in terajoules, but I think it's more speaking because we know what the oil, a liter of oil, now it's gigaton of oil. This consumption is represented by this, can you see my I think, yes, you can see it by this small block here, compared to the complete annual solar radiation on the Earth on this big block that represent, in fact, 6,000 tons, 6,000 times the world consumption. And these are the proven reserves in terms of wind, the big box here. Then biomass comes second, the green one. You see that even biomass, it will, in terms of potential, it's greater than the current consumption. Of course, we will not exploit all of it. But that being said, it means that we will have enough renewable resources to replace coal, oil, gas, and uranium, which are also represented on this little block here. But coal is quite the biggest part. I know that India is still relying on coal, like China, but really there's a move to be made. And biomass is part of the equation. And biomass is the only renewable source of carbon. People tend to forget that. The other renewable energies are not based on carbon and they are intermittent. Biomass can be a constant source, a constant supply of energy, of renewable energy. Also, in these human activities, about 15% of it is electricity, and that's growing, and it will grow in the future even more. Now, if I go to the next slide, this is rather recent. I looked at the IEA figures. It comes from the World Energy Outlook. You can download this report from 2025. So rather recent, it shows the progression of our consumption, and of course, at the same time, the progression in emission, gigaton of carbon dioxide. You see now nearly 40 gigaton now. And when you take CO2, and if it says 3.87 or so, 1 ton of carbon, equates to 3.87 ton of CO2. So if you divide by 3.87, you come to 10 gigaton of CO2 of carbon. And if you compare this 10 gigaton of carbon to the previous value, you can see out of the 15 gigaton of oil equivalent, that makes quite a big amount. It means it's nearly all, of course, it's all fossil fuels. Only uranium and water, so hydro, do not emit carbon, but the maximum part of our consumption produces CO2. That's what it means. And we see the scenarios, how it has grown since 2010. Now we are here, and they want to go to this route. So current policy scenario, if we do nothing, if we continue with the current policies, CPS, we will go this way. So it will start to reduce in 2030 or so. But we should go steps. That means stated policy scenario in order to reach the limitation of 2 degrees Celsius by 2050. But yeah, to me, this is quite impossible. But I already saw, we had already such figures 10 years ago when I was still teaching to my students, and I was telling them, there is no way I see a curve going sharp like this, because nature does not force discontinuities. We are continuous. And this is what happened in the past, in fact. So in any case, I say this because we have to be optimistic still, because we have carbon removal solutions, and we should use carbon removal solutions. Agriculture and waste on this 42 gigatons per year. I said 38, but 38, it's only CO2. If we include land use or deforestation, it comes to 42. And if we include methane and nitrogen N2O, so nitric oxides, N2O, we say. If we include those gases, it equates to 50 gigatons per year. So 30% of this 50 is agriculture and waste. Carbon removal is a very important way of reducing this amount. A little bit more detail. This comes from the FAO, so FAO organization. We can read on the report that the total agriculture and waste emits, so the 30%, that's 16.2, in fact, billion tons of CO2 equivalent. It increased by 10% since 2000. And you have the detail here. 48% is farm gate and livestock, and mostly from methane also, and nitrous oxides. So land use change is free, about, primarily from deforestation. And pre and post-production, that is processing, transport, and packaging, is about 1/3 of the total. And if we only take the waste-specific part of this, that would contribute to about 10% of the total greenhouse gas emissions, with rotting food, landfills, significant methane. Methane, you necessarily know, is a very, very strong greenhouse gas. When you count methane, you have to count the number of years it will stay in the environment. If you count methane on a 30 years time frame, that is 30 years from now, the total contribution compared to CO2 will be 100 times. So 1 mole of methane equates to 100 moles of CO2. But if you count it on a 100 years time, which people used to do and continue to do, it's less than that. It's about 35. Of course, we do not have 100 years in front of us. So that's why I prefer to say it's 100 times, even 120, depending on the calculation, times the carbon damage to the environment. So there are two strategies to reduce the impact. Either reduce the emissions at the source, so be more efficient, use more renewable energies. And the second one is to remove carbon from the atmosphere in order really to reduce CO2 from the atmosphere, which at the current level is about 400, a bit more than 400 ppm. There is only one way, in fact, is to remove carbon. Today, there are a lot of initiatives. There is one very, very important initiative in Switzerland where a company is just taking filters and filters the air to remove CO2 and then use the CO2 to produce combustible material or to produce fuel. But we can use biochar. Biochar, I will explain later, belongs to the second group of removing carbon from the atmosphere. I have a short video here. I hope the sound will come because sometimes I have to do something with the way I share the system. I have to share. Yes, you see, the sound is, so I have to share stereo. That's it. Now.
Professor JB, you
Yes.
do share sound, and that will also
Yeah,
come.
I just did. No,
Okay.
I have to share. I have to share the sound of the YouTube for one. That's why. But I will do it now. It's coming now. Okay, this one. See if it's coming. Now I have to share the screen. Nouveau partage. Now you should see the TED one. Yes, you see it.
Biochar is essentially carbon that was captured from the atmosphere by plants and transformed into a very...
Could you hear the sound?
Yes, very clear.
Okay,
Yes.
great.
very stable form of carbon. It looks like charcoal powder. The first amazing property of biochar is that it remains stable for hundreds of years, even if put in the soil where biomass would normally degrade. Think about it. The CO2 captured by plants through photosynthesis and converted into biochar stays in the soil and so stays away from the atmosphere for hundreds of years. So we have a carbon removal solution, and this is good for the climate. The second amazing property of biochar is that when mixed with topsoils, it improves the soil quality, hence crop yields. This is especially true for poor, dry, and acidic soils that lack nutrients. Putting carbon in the soil has been known empirically for hundreds of years as a way to improve soil quality. It was used in some parts of Amazonia prior to the arrival of Europeans, and it's still used today in some part of Asia. Biochar's effect on soil comes from its microstructure. When magnified, biochar looks like a carbon sponge with hundreds of square meters of surface per gram of biochar. This ultra-porous structure helps retain water and nutrients. Biochar also favors the development of microbial life into the soil that is most needed for plants to absorb nutrients. And last, given its high pH, biochar helps counter the negative effects of soil acidity. Using biochar allows to reduce or even eliminate the need for fertilizers, cutting costs for farmers and helping the environment. And the great thing is that given its stability, biochar needs to be applied just once and its effects last for decades. And then there's a bonus. The production process of biochar generates flammable gases. Part of those gases are used to heat the reactor where biochar is produced. And the remaining gases can be used to generate renewable heat or electricity. So not only the production process of biochar is self-sustained, but it is a source of additional renewable energy. Quite incredible. So we have this amazing product that is a climate solution, an agricultural solution, and a renewable energy solution. And now you start to wonder, how come this biochar thing he's been talking about is not widely used all over the place? What's the problem? Well, the answer is plain and simple: costs. Most biochar produced in the last years had to be sold at prices as high as $1,000 per ton to cover production costs. That made biochar uneconomical for most usages. And so, despite its wonderful property, it has remained a niche product. But things started to change in the last couple of years. The recognition of climate change started to shift our behaviors, leading companies and states to commit to net zero trajectories. Some innovative companies committed to an accelerated net zero trajectory, started to buy at high price biochar-based carbon credits for their long-term CO2 removal effects. That changed the economics of biochar, as all of a sudden the climate benefits of biochar could help subsidize its agricultural usage. As a consequence, biochar is emerging as a credible CO2 removal solution, especially that it is one of the very few that is available today for scaling. The technology is mature, the scientific backing is here, the economics could work. And the potential is huge. In Africa alone, we estimate that 500 million tons of agricultural residues are available to produce biochar. That means about the same amount of CO2 being removed every year from the atmosphere. And there are many more billion tons in the rest of the world. So let's make biochar a solution at scale. For this, we need three things. One, access to biomass. Biochar production requires large quantity of dry biomass, ideally sourced close to the production facilities to avoid transportation costs and emissions. It needs to be residual biomass, so it does not require additional land to grow it. Most biochar companies today use wood residues like sawdusts or branches to produce biochar. But many alternatives exist, in particular agricultural residues. Two, we need super efficient 24/7 production systems. The technology exists, but there's still room for improvement. And three, we need to encourage farmers to use biochar so that they can reduce the usage of fertilizers and improve crop yields. Many companies, as we speak, are developing biochar-based business in a variety of geographies and with a variety of feedstocks. I co-founded one of them. We focus on tropical developing countries. Biomass is super abundant there in the form of agricultural residues. We used an optimized production model with easy-to-operate, mid-sized production plants where the pyrolysis reactor looks like a tank wagon. Soils in the tropics are generally poor and acidic, hence benefit the most from the addition of biochar. And last, energy generation is most needed in rural areas of developing countries, where very often less than 25% of the people have access to electricity. That's how we go back to Mr. A1A. we will convert to biochar the leftovers from his coffee cherries so that he can use it in his fields to improve the quantity and quality of his production. Mr. Ewane will be able to afford the biochar, given that it will be highly subsidized by the related carbon credits. And the electricity generated will be distributed locally. A very circular model for climate and people now. Thank you for your attention.
So, I hope it's
Professor
okay.
JB, before you start, I would just like to let you know that our Director of Research is over here and our Dean PGS have also joined. So they are all listening to you at the moment. Okay, we are not able to hear you. We are not able to hear you. Please unmute. Professor JB, unmute.
Yes, I know, because I had to stop the sound of the video. That's okay now.
So
It
we
should be
have
okay.
our Director of Research and our Dean PGS who's also joined in. So they are also listening to you. So I welcome our Director of Research, Dr. Shivramo, and I also our Dean PGS, Dr. Venkatramana. So for the program, because of them, all these we were able to arrange. Thank you very much. Professor, you can continue. Thank you.
Yes, thank you for participating to my talk. Humbly, I will try to explain what I know, and surely many of the people in the audience complement what I will explain now. I will continue sharing my screen. It was here. Ah. So the person you just heard is the CEO of the company Net Zero Green. One moment, try to. Voilà. It's a TED talk. I happen to know him indirectly, Mr. Raymond, because I came across his innovation. His innovation was labelized by the Solar Impulse label. He got the Solar Impulse label and is very active now in Africa. I would hope he comes to you in India because his solution is quite innovative and interesting in terms of cost as well. So how does it work, pyrolysis? Biomass pyrolysis, because there are other forms of pyrolysis. Pyrolysis can be used for biomass, it can be used for coal, it was used for coal, it can be used for plastic. I'm currently working on plastic pyrolysis very extensively, and it can be used for natural gas. People forget that. We could also pyrolyze natural gas, produce hydrogen, and leave the carbon, also leave the carbon in to do something else, like carbon fibers or other fillers for tires, for instance. But now we will speak mainly on biomass pyrolysis, which relates to the thermal decomposition of organic material, because biomass is organic. It occurs without oxygen, without added oxygen, because in biomass you have already 40% of oxygen bound to the structure. So this oxygen will, of course, when you heat it up to a certain temperature, above 300 degrees Celsius, the material will decompose, but will also create chemical reactions inside its own material. It will consume itself, in fact, you could say. And you will produce biochar, biocoal, and bio-oil. So very simple. You take biomass residues, you have some form of reactor. It can be horizontal, vertical, batch, continuous. You need a heat source, typically above 300 degrees Celsius. And there are several ways to transfer the heat to the biomass. Many different ways. I will explain a bit later. So what we want to produce most biochar, a little bit of bio-oil, and biogas or syngas is a byproduct also. and can be used, as Mr. Raymond said, to heat the reactor, or it can be used to produce electricity, or both. Now, this comes from a publication where you have the link here. Biomass is composed of three main parts. It's more complex than that, but we usually distinguish between hemicellulose, cellulose, and lignin, coming from the lower bound material, which is hemicellulose, which starts to decompose at 240 degrees Celsius. So it will break the bounds of biomass. Then cellulose will decompose, and at the end, lignin also, with an increase of temperature. You have some kind of TGA curve here, along with time, starting at a low temperature and finishing at the end temperature with the release, in fact, of the material here. The release will produce biochar, as I said, and of course biogas with those gases here. Part of the bio oil, and it's a bit oversimplified, because when you heat it up, when you do torrefaction at low temperature, which speak about it, 300 degrees Celsius, 340, the bio oil will mainly be composed of acetic acid. So you could not really say that it's bio oil. It's acid it's wood oil, in fact, wood acid. Advantages, it has been stated by the speaker, the potential global removal, 0.5 gigaton of CO2 per year, up to 2. So it was stated that this equates 0.5, in fact, equates to the amount of carbon that we put, the increase of carbon that goes to the atmosphere in terms of CO2, in fact, as a net amount, because it's more than that, but part of it is already absorbed. What is remaining and increasing the ppm level of CO2 is about 2 gigatons of CO2 per year. So this it also reduces the methane emission. It reduces the nitrous oxide emissions. Doing that, because it avoids this agricultural waste to produce these greenhouse gases. We heard that the stability is more than 100 of years. Fertility is increasing, and if you go into detail, you see that, in fact, it also allow to increase the availability of nutrients like potassium, calcium, nitrogen, and phosphorus, which are very necessary for plant growth. And due to this very, very porous structure, there is a better water retention, increasing the porosity, improving the drought resilience. And last but not least, improved microbial activity, giving a surface for biofilm production. In Switzerland, it's quite popular to use biochar, but only if you do bio-agriculture, if you produce bio-food, certified. Most people don't use it because it's too expensive today, still too expensive. More than 1,000 euro per ton, as we have heard. Think about it, fertilizers do not cost that much. And also, if you want to offset it with the carbon credit, the carbon CO2 today can be purchased as carbon credit. The range is 20 to 40 dollars, if you say euro per tons. Some countries like Switzerland, it is more than that. It was increased to 120 because of policy regulation, local policies, but on the international market, the price is much lower. So it cannot offset $1,000 per ton. It's impossible today. So we have to reduce the cost of biochar to a few $100s per ton maximum. Why is it not going? Yes. So there are three main types of pyrolysis if we distinguish between the temperature and the time, residence time. Most used is slow pyrolysis with the temperatures in range of 300 to 700 degrees Celsius. The heating rate is rather low, 1 degree Kelvin per second. So the retention time will be 450 to 700 seconds. Typically 20 minutes, you would say. 20 minutes to maybe a bit more than 20 minutes too. Intermediate pyrolysis, where the heating rate is faster, retention time is much less than 1 minute, and fast pyrolysis, flash pyrolysis, where you have higher temperatures and much higher heating rate. But to achieve this heating rate, you also need to have smaller particles. There you have a powder in this flash pyrolysis. There you should have small particles. Otherwise, the heating rate will not work because the heat transfer inside the biomass particle will not be so high. So most processes today are in the range of slow pyrolysis. In the old times, it was even slower than that because perhaps you know, in the old time, we would produce biochar, biocoal in the forest in a closed enclosure, in fact, built on site with bricks, and you would put fire under the pile of the wood, and after 1 day, you would come back and get biocoal. This also happens in your fireplace. At the end of the combustion, if you stop the combustion, you will get biocoal. Probably every one of you have experienced that outside or inside the fireplace. So I did not want to avoid speaking about this your own biochar production facility from the project by Professor Rinku Verma in the Department of Forestry and Environmental Science. This unit there that I've been visiting, very interesting way of producing biochar, but perhaps not fully optimized. It will require additional optimization for energy production and for heat transfer. The big problem is to ensure heat transfer. The good thing about this unit is it is using waste as a heat source, and that is the way to go. You should not use, of course, fossil fuel because it will defeat completely the purpose. Then also one additional advantage is that it uses the gas, the biogas, to heat the material, which is also a good thing, recuperating the gas and not burning it outside like it was done in the old times. So there are three main stages in the pyrolysis. Well, I forgot to say before here that there are batch processes or continuous processes. Most processes available today commercially are continuous processes. They can work 24 hours per day, but they are generally more expensive than batch processes. The one that you have is a batch process. I really believe in batch processes also for plastic pyrolysis because they are cheaper, but it requires innovation to bring it to a stage where you have a very good efficiency. So in both batch or continuous, you will have the three stages. Fixed drying, so biomass usually have some humidity, some moisture. You can first dry it outside under the sun, which you do there at the university, which is the easiest way. But then there is remaining moisture. So there will be first phase of complete drying before you can get thermal decomposition and then separate the product into the various phases by condensation. I show you here one first example that Professor Verma knows because it was in Switzerland, a very large, a big project that I conducted, which was called TOR plant. It was for mild pyrolysis, that is for torrefaction. We had several stages. You can see the dryer here, which is a dryer with a screw system. Same for the pyrolyzer with a screw, the refactor. And then the gases are going out of this system. There is a burner system here to produce heating oil, in fact, at the temperature of 250 degrees Celsius, that would be used for drying and for torrefaction. And the torrefied gases also goes to the dryer here to improve the drying, even go in the grinder here to start drying. This was working with wood wastes, and we were producing about 100 kilos an hour of torrefied biomass continuously. But this process itself, although it was a very, very interesting way of doing it, was not optimized, and the project did not find investors to go further, unfortunately. I show you here a three-dimensional view, very compact, so it could fit into it could be fitting into a container, a 20, 40, in this case, 40 feet, we could put it in a 40-feet container. And this was the realization there in Switzerland, where we had first we had the raw biomass storage here, then the torrefactor. Only see the end of the torrefactor, the thermal oil heater, using the gas from the torrefaction, the turbo compressor. It was quite innovative, maybe too innovative for what we wanted to do. A flux burner that is a flameless burner using a reverse turbine. So the turbine, we use that as a turbo compressor to force the gases, in fact, to suck the gases through the system. And a screw cooler for the torrefied chips. Power supply and control. Big part here in any of this system is to have a very, very, very accurate control of temperature along with the time. Another example which I came across was in a European proposal submitted in 2023 to the European Horizon program with a large number of participants, in fact, where we also had the drying phase, pyrolysis phase, also a mild burner that is a flameless oxidation burner for the biogas. So very similar scheme, in fact, that what you saw before, but this was to produce biochar, not to produce torrefied, but biochar. So the temperature was about 400, 500 degrees Celsius here. And the biochar would be the whole unit, in fact, would fit into a lorry. The idea of this project was to move the unit from place to place where the waste is available. Okay. And from this mild burner, we would have a tri-generation system, would do cooling, heating, and produce electricity. This is very nice on paper, but very difficult to realize we had one company that was able to do that, company Marconi. You see the guy, he was exposing this unit. You can see that it's on a lorry because you can distinguish here the tires. It's a big lorry. I don't think they were successful in selling it so far. But this company is a very innovative Italian company. There are other ones I can think about. The other ones are, for instance, Pyrec.
Battery is running low.
You heard about it, Riku. I've been in touch with them. They sell modular units. They have good. I think they start to have an expansion, 0.5 to 2 tons of biomass per hour. Syncraft in Austria, rather small plants. They produce electricity as well. They produce heat and power and biochar. The one you just heard with the video, Net Zero, they started in Brazil and Cameroon. Cameroon with a small unit. He was in the video. In fact, he speaks about the Cameroon experience with coffee beans, coffee spent, not the beans, but the coffee kernels. And he has containerized units for these residues. They start to be successful as well. They are raising money to go to the next step of expansion. And I did not know, but looking in the internet, I found Biochar. I don't know how you pronounce it. In the UK and India, they have micro pyrolysis residue reactors for small farmers. Maybe this is something you should look into as well, as it is also located in India. Now, there are some challenges, of course, starting with the feedstock logistics. Pyrolysis plant, they require a reliable and continuous supply of organic waste. And in reality, the resources are often geographically dispersed and seasonal. So if you have to transport biomass over a long distance, that will increase costs and reduce the sustainability of the process. So it has to be, you have to have a local unit. And the problem also is feedstock preparation. You need drying, shredding, sometimes cleaning before entering the reactor. High moisture content will reduce energy efficiency and make reactor operation unstable. So the preparation, it's often the case with biomass, and the feedstock logistics is a very, very big challenge. Another one is reactor scale-up. So reactor engineering, reactor scale-up. Pyrolysis reactions are very sensitive to temperature, to heating rate, and to vapor residence time. So you need to make uniform condition inside the industrial reactor. This can be quite technically demanding. Many technologies work well at pilot scale, but they require careful engineering to operate reliably at industrial scale. I advocate in a case for smaller scales, medium scales. There are companies doing very large installation, but they use wood waste where they are available, and there are units that you will not move from place to place. But it is a complete different business model. Really, what we need are units that you can move from place to place, or units that you can duplicate at a small cost, or series production of the units, and not industrial scale, basically. Large scale, I mean. Industrial scale in terms of repeating the unit several times, the same units. Last but not least, you have also the certification problems. The properties of biochar depend strongly on the feedstock and the pyrolysis condition. So for agricultural use and carbon market, biochar has to have strict quality standard. So ensuring consistent product quality across different plants is essential. In Europe, there is certification scheme. There is also an international scheme, IBI. But in India, for instance, there is no certification of biochar. This is something that the government should work on if you want to use it at a large scale and repeat it. So these are the IBI and EBC standards. One problem are the contaminant and the heavy metal limits. You cannot have a higher quantity of heavy metals. They should stay below the limit usable by plants. And also, you cannot put biochar every year. You put it once and for all. If you repeat it, you will accumulate the biochar into the soil, and that's not really needed and wanted. So there are the sustainability consideration as well. It complements what I just said. So the use of agricultural and forestry residues, mostly that, and not wood, for instance. You should avoid competition with food production and use sustainable harvesting practices. The question of life cycle emissions. So transport and drying energy should be kept to a minimum. And the net carbon removal will depend on using a full life cycle analysis. And very few companies are doing a full life cycle analysis. In fact, they just do a reduced one. Energy recovery, of course, you should use everything that comes out of the system in terms of heat and energy, mainly heat, in fact, and gas, the biogas. And avoid, of course, land use and increase biodiversity by doing it. And of course, protection of natural ecosystem, soil carbon enhancement, and contribution to a regenerative agriculture, avoiding the use of fertilizers. I was discussing with my neighbors, who is going to be our next mayor of the city. Jean-Louis Barras is a farmer, in fact. And I asked him what he thought about biochar, and said, yes, it is good for agriculture. It is good for bioagriculture, and it helps not using fertilizers. Of course, biochar itself is not fertilizer. It does not do the same as nitrogen. But nitrogen you can easily put into soil by rotation of the crops, putting some plants that will bring nitrogen to the soil. And that is a well-known practice, has been practicing for over centuries, more than centuries. Now we tend to use a lot of fertilizers, but that will kills the soil. We know that. Future potential. So the good thing is that the carbon market are going more and more, and we have seen the IEA tendency. We have seen the Paris Agreement. The bad thing is that some countries are going back to the Paris Agreement. One big one you probably know has denounced the Paris Agreement. President Trump is not in favor of doing that, but most countries, especially Europe, is pushing for carbon removal credits and durable CDR as well, carbon removal. And biochar should be recognized as a high durability solution. So the integration of agriculture, I just said, improves soil fertility and water retention, increased resilience to drought, and circular use of agricultural residues. We had information about removal. The decentralized system should be near the biomass sources, and there should be synergy with renewable energy and waste management. when I say synergy with renewable energy, we could also think about, and it exists as a pilot and as a development, using solar energy, using concentrated solar energy to heat the reactor. I think this is the way to go, using, for instance, a parabolic through used today to produce steam and produce power, but you could use the same concept with the reactor located inside the parabolic through at the concentration point of the sun to heat the reactor, therefore preventing the use of waste. That we could use the waste better to produce biochar instead of energy. Now, why is it matters for the planet? Now, we know that, of course, as a concluding remarks, climate change mitigation, first of all, converting atmospheric carbon captured by plants into stable soil carbon, which is the most efficient way of doing it. Of course, you can try to take the CO2 out of the atmosphere, but it is like emptying the sea with a small spoon because there's so much CO2 everywhere. But in this way, we can do much better carbon sequestration, and at the same time, with all the other advantages, with the potential global removal up to 2 gigatons of CO2 per year, which is a very, very big amount. So it is one of the most durable carbon removal solutions. Sustainable waste management, transforming agriculture and forestry residues into valuable products, because producing biochar, putting it in the soil is one way, but using the biochar to produce activated carbon or to replace coal into steel factories is being done today. Is also another way to use the forestry residues and agricultural waste, and at the same time reducing methane emissions and supporting circular bioeconomy. Last but not least, of course, resilient agricultural system, so to have soil that will keep being fertile and retain nutrients, increasing the water holding capacity and resilience to drought. I guess these are very important factors for India and for tropical countries in general, and supporting regenerative agriculture. Now, there are some links here as conclusion. I've been shorter than one here, Rinku, but that will leave time for questions. Of course, the World Energy Outlook. You can look at the IBTC Council. I don't know if I click on this, it won't show, but I will nouveau partage. I think I can reshare this IBTC Council. This is the one here. I've been part of this council. I've been part of this council several years when I was working at the Swiss University. It's International Biomass Torrefaction and Carbonization Council, and it will have it has a number of interesting members. In fact, I know very well Michael Wild, the president, and you see the team here, but most of it the members, and you can have where are they? Sorry, I have to do that. I think the members are on the bottom. I don't remember. No, sorry. Never mind. Yes. And what's interesting is they were not very successful in Europe because torrefaction lost interest for a number of reasons. But now there is a very strong interest in Eastern countries, in China and in Asia, and you can see the type of development they are doing. And there is an international biochar association as well. So on these things, I will stop my presentation. I thank you for listening to me. I hope it was not too long, but that leaves time for questions. And I am open to that, Rinku.
Professor JB, thank you so much. And I will just ask if our teachers and scientists faculty are having anything to ask. Any of you would like to ask Professor JB any questions or anything? You can
I can't hear you very well.
ask.
Can you go closer to your mic?
Yes, I was just asking our faculty and scientists if they had any questions to ask. They are most welcome. They can come close by because then it would not be close for Professor JB to listen to you. You have to come close to the laptop. Anyone has any
Yes.
questions? Anyone has any questions? You can ask. Yes, come. You can come here. We have a young entrepreneur, Apurva. She will ask you. She was in
Okay.
Australia. She's come back. She's an Indian. Apurva, you can talk and you can put your question to Professor JB. Come close by.
Hi, Professor
Yes.
JB. How are
Louder,
you?
Hi.
louder.
Good morning still, yes.
So I have a question regarding the bio oil, Professor. So how is it currently stored and where is its applications?
The bio oil or the biochar?
The bio oil.
The bio oil is a
Yeah.
byproduct that you would like to avoid, in fact, uh, because if you want to produce biochar, you will not have too much bio oil, but you will always have some bio oil produced. And the problem with bio oil is that it is not stable. So you have to it will oxidize. It is subject to oxidation. So if you have bio oil and you want to use it, either you use it directly, you burn it in your system. That's one way. Or if you have large quantity of bio oil, which also one way to use pyrolysis, not to produce biochar, but to produce bio oil for as a fuel. That is being done today by some companies. But these are large plants. These are not small plants. In this case, they will refine the bio oil. They will have a refining stage later. It's exactly the same with plastic, but if the goal is to produce oil, I would rather go to plastic pyrolysis because there is much more oil coming out from plastic pyrolysis than from biomass. Biomass, the problem is oxygen content. So your bio-oil will not be stable. So you need to have a good refining step behind or burn it directly. Yeah, you're welcome.
Okay.
Yeah.
So if you're going for a commercial biochar plant, what type of machine, a biochar production machine do you recommend where the bio oil is less and we have more of the biochar yield?
Yes. Yes, indeed. Of course. It would be interesting to speak to Mr. Raymond if you want to go to this. So, the CEO that I have been showing you, you can easily go to his website.
Actually, at 500 degrees above 500, 550 or 600, 550, you will get more of biochar and you get less
Yes.
of oil.
Yes, of
So
course. Yes,
depends
yes,
on the
yes.
heating, the temperature at which we are heating. So depending
Yes.
on that, if you have a high temperature,
Yes.
more of the biochar and less of the oil.
Yeah, but yes, you still need a use for the oil. Yes. You cannot leave it like that. You have a small amount of oil, but you have to take care of it, of course. The best way is to have a burner that will burn both the gas and the oil. One way is to avoid condensation. So you keep on your lines. That what we were doing in Switzerland with torrefaction. We did not have any oil with torrefaction because the whole thing was kept above 300 degrees Celsius, 250 about. In that case, there was no condensation. So the whole byproduct was gas.
Okay.
And then if you keep it gas, then you can go directly to a burner and you avoid the condensing. But in this case, you have to be very careful that your whole line is staying hot so that you don't have clogging because the oil will clog all your system. That's the problem. Yeah.
And I have one last question. So, how do you determine the longevity of biochar in the soil?
How
The
do
long,
we?
so how do you determine the longevity of biochar in soil? For example, how do you determine this biochar in the soil has an impact for 10 years, for 100 years, for
How long the
1000
biochar
years?
will
So, how do you
remain?
determine
Yes,
that?
yes. Well, it is. There have been a lot of studies already for that. It is known. Only this is a specific agricultural practice. I am not a specialist in agriculture. I've been doing it myself for roses, for my garden, but uh, you know, the Mr. Raymond was saying that it was practiced in Amazonia. It was called terra preta. Terra preta, they were burning on site. They were burning the crops and keeping it as a powder biochar, and it was going into the soil. And they found that the places where they were doing that compared to the places where they were not doing it were kept fertile. And in the other places, they were not fertile at all. So this where it started to think about biochar as a soil amendment. But yeah, it has to be mixed with the soil, uh, with good agricultural practice that normally use with a small rotation on a surface. It does not need to be very deep in the soil. But again, I am not a specialist on that, so I could not really give more detail.
No
Okay.
worries. Thanks a lot, Professor. Been helpful.
All right.
Thank you so much, Professor. Any other faculty, teachers? Yep. So you can come here with your question. We have one more, I think, entrepreneur, yes, who also wants to ask you.
Okay.
Close by from here.
Okay. Morning, Doctor. My name is
Good
Nitin.
morning.
The reason my question is slightly different because I hope you don't feel offensive with my question.
No problem.
Yeah, no. I just drafted instead of focusing mainly on the biochar as a carbon removal pathway or a process. My question is that should we also emphasize on technology that improve the energy efficiency and reduce the emission upfront? You know what I mean? I'm talking about
Yeah,
the
of course.
source, controlling at the source itself rather than
Yes.
looking at the process-based kind of an emissions.
Of course. Well, this is not an offense. It was part of my slide. There are two strategies that are complementary. The first strategy, of course, is to avoid emissions. You need to avoid the emissions. Avoiding emissions, that means using renewable energy. Of course, we have enough renewable energy today to replace all the fossil fuel. It was part of my presentation. We don't need gas. We don't need uranium. We don't need coal. We don't need gas. We have enough energy. The only thing is a question of will and technology availability and transformation. But having done that, we still have 400 ppm CO2 in the atmosphere. We need to reduce this 400 ppm. Otherwise, the climate will continue to warm up. So one way to reduce is biochar. The other way is carbon sequestration and usage. Carbon storage and usage, which there are a lot of projects today to do that. Huge amount of money that are being spent on that. People focus on that rather than focusing on using renewable energy. So there is also a challenge You have money for R&D, you have money for development. Where do you put your money? The money is limited. The money is the effort you can put in it. The problem is, what is the most efficient way of going from there to there? And you should not do too much on one because you don't do on the other one. So it's a question of equilibrium of resources. And I think all ways have to be taken into account. And we should not put so much energy into carbon sequestration by other means. I mean, CO2 removal from the air is it's I think it's a waste of energy, but that's my own opinion, you know. Yes.
Yeah. So you rightly pointed out that money is very important. So basically, being an entrepreneur, for me, money is a capital, right? So
Yeah, of course.
I think I do agree with you in terms of your last statement when you talk about rather than focusing on the carbon sequestration, we need to talk about the capital investment. So now,
Yeah, of
from
course.
my point of view, and maybe you can educate me more on this, I strongly feel that when we look into the impact part, can you hear me clearly, first of all? Can you hear me, Professor?
Yeah, I can hear you. Yes.
Yeah. So what you said, I just try to align with your thought. Could improving efficiency through advanced materials, I repeat again, could improving efficiency through advanced material, sometimes we have a larger near-term impact that carbon removal strategies are not more important rather than efficiency utilization in terms of using an advanced material. What I mean by that is that carbon fiber, because the world is talking about carbon fiber composites. You mentioned in your presentation one of the half of the element of the techno machinery are based on, for example, turbines. They are made of composites. So my point of view is that building up a turbine in your whole machinery models based on efficiency, we are talking about not removing the carbon completely, but also talking about using a lightweight kind of advanced materials like carbon fiber, or maybe talking about, depending on application, aramid or Kevlar. So in my opinion, talking too much about carbon removal is not the only solution. That's all.
Yeah, of course. I completely agree with you. My talk was about soil enhancement, agricultural practices. But if we want to use carbon efficiently, we should use natural gas. Pyrolysis of natural gas, producing carbon as a material from natural gas, and using hydrogen from the natural gas as a power source. We have enough natural gas, and I had a presentation on that last year in Portugal, showing that if we use natural gas in the efficient way, we avoid completely the CO2 emission because we take the carbon from the natural gas. Today it is being done. There are few pyrolysis projects. It is using pyrolysis. It is not using steam cracking because today hydrogen is made by steam cracking of natural gas, which is crazy because you put a lot of CO2 in the atmosphere. So instead of doing that, and that is efficiency, as you stress it, you have a material that is carbon. Carbon, you can use it to replace steel with carbon fibers, of course, and we should have everything made of carbon rather than of steel in this case. But the transformation of the economy is very, very difficult. There are few companies, at least 2 or 3 companies in the world doing that. They started using natural gas to produce hard carbon. In fact, their goal was to produce hard carbon, was not to produce hydrogen. There is at least one big company doing that, and the hard carbon is used for tires as a material. But again, it is a capital-intensive economy. It is not a circular economy. It is a linear economy because you produce tires, and at the end of the tires lifetime, you burn the tires. So it defeats the purpose. So I agree with you, efficiency is key, but the other thing is circular system we need because efficiency will not be enough. You can increase the efficiency of the system, but if at the end of the lifetime you just put every carbon in the atmosphere, it will not be useful, you know.
Sorry, no, you complete. My point is, if I look from an investment point of view, you said that building up a capacities for only the carbon will not be sufficient. It is capital intensive. I do agree, but I come back to the core issue of the problems of the emissions.
Yeah.
As an entrepreneur, do we invest our capital on carbon removal process like talking about biochar, or should we focus on efficiency-based advanced engineering materials? So the solution lies not in the capability, but building up the capacity in terms of advanced engineering materials. For example, in a country like in India, we do not have a single manufacturer which can produce an advanced engineering materials. So it cut short. What I'm trying to say is that, yes, from an agriculture perspective, we look from a kind of a mediator, which is biochar, is an excellent. But if you look the larger impact on a more industry, because agriculture is also a kind of a food industry, I think focusing on advanced engineering materials and then talking about efficiency as a capacity, not as a capability.
Yeah. Well, I agree with you. And what is important as an entrepreneur, what is the goal of an entrepreneur? An entrepreneur wants to make money, right? So if it's only your goal, it doesn't matter what you do. Now, if you are ethical entrepreneur, what I hear from you, what is the most impact you can make on the environment by being an entrepreneur? What is the best use of capital investment? Then the solution is not unique. There is no one solution for all. Everything has to be done. So you need entrepreneur like you that will focus on materials. I agree that India is not the only country with such problem. I've been in Morocco. Morocco is importing all the technology. They don't produce. They started 20 years ago with the new king, Mohammed VI, to improve their process. So not to rely on external purchase, but doing themselves. They started to doing that. Like for instance with concentrated solar plants, which is a very, very big impact for them because then they don't import oil like they used to. The key issue to start with is power generation, also for India, not relying on coal. And how do you do that? You develop renewable energy. You improve materials because you need good materials for renewable energies. You need a lot of materials that are innovative, but you also need good processes and factories. So producing power photovoltaic rather than buying photovoltaic from China, like we do in Europe. Producing wind turbines rather than buying them from Norway or whatever else. Producing a system that produce renewable energy, renewable heat and cold. And with this power, you can then feed your factories to produce more materials, to go to more automation, to increase robotics, to put more robots into the system. It's not the problem of India today, but many countries are facing labor shortage and they need robots. But that's another world together. The world of 20 years from now, it will be completely different as the world of today. Completely different. We cannot imagine what it will be.
Thank you very much.
Thank
You're
you so
welcome.
much,
Thank you.
Professor JB, on behalf of the University of Agricultural Sciences, our Dean PGS, Director of Research, our scientists, faculty, students, and everyone here seated. I thank you wholeheartedly, and I'll be sending you the pictures so that you will see our participants. And
Okay, great.
I thank
Yes.
you very much. And we all will just
Thank you.
thank him loudly so that he can hear. They're all clapping for you. They're all clapping for you. So thank you very
Okay, I
much.
do that too.
Please be online because we have Dr. Anand who has already joined from the Indian Institute of Science. So now I just call upon Dr. Anand, quickly reading to you his short CV so that you are aware of what all he has done. So Dr. Anand M. Shivpuji is a senior research scientist at the Indian Institute of Science, and he has a PhD in non-regular fuels in ICE. He's under the sustainable technologies, and he works with gasifiers and gasification. So he's a highly motivated individual, passionate about research, and over 20 years of rich academic, industrial, and research experience. Dr. Shivpuji's experience has enabled him to create a challenging and a thought-provoking environment, enabling the evolution of elegant but simple, non-intrusive solutions to complex proto-practical problems. His core interest is in the field of generation of bio-derived chemicals like biohydrogen, biosyngas, biomethanol, etc., and their utilization in energy conservation systems. Okay, and fuel cells and internal combustion engines. Prognostics and health management of thermal systems in general and fuel cells and particular is the key focus emerging from the field of current Dr. Anand's interest. Current employment is with the Thermochemical Group at the Center for Sustainable Technologies, India, and he's also at the Indian Institute of Science as a senior research scientist. The position mandates handling a range of sponsored and consultation projects, interaction with the research students, and engaging scientific sessions. As a part of the core team, Dr. Shivpuji has first-hand experience in submitting and defending a range of proposals with the government agencies like DST, MNRE, DBT, and private organizations like Tata Motors, and defending a range of proposals with the government agencies, which I already mentioned, Tata Motors and other agencies. He is also active in corporate and academic training on tools like OpenFOAM, CHEMKIN, Python, etc. Dr. Anand is a strong believer in open source philosophy. He has developed and continues to host the website, a non-commercial online platform, which I can share with you, addressing thermodynamics and fluid dynamic aspects, a range of online tools, numerical codes, and fundamental concepts discussions in white paper and preservation are hosted on the website, and the site continues to evolve with time. So with all this information, I'm very, very happy that Professor Anand has made it. Though he was not in Bangalore, he would have come in person, but traveling to other place, he has given some time to us. So I am welcoming him, and I just will give over to Professor Anand Shivpuji to speak to you all. Just a minute. Sir, just a minute. I will, spotlight so that our viewers can see you. Yes. So we have Dr. Anand M. Shivpuji, who's a senior scientist from the Indian Institute of Science. So over to you. Thank you very much. We have our faculty members who are seated here, and they all will clap for you so that at least you can hear them. Thank you so much. Thank you.
Hey everybody, very good morning. This is Dr. Anand here from Indian Institute of Science. Sincere thanks to Dr. Rinku for giving the introduction. Without much ado, since I have already indicated I'm a little short on time, I would like to, with all of your permission, would like to jump into a small presentation that I have put together, wherein we'll be discussing a little bit regarding some aspects related to biochar. I will not be doing deep diving into the philosophy of this biochar generation. It will mostly be a cursory treatment, but then anyway, it will give you an overview of how exactly we, from a technical perspective, are perceiving biochar. So let me just share my screen.
Yeah.
Is the presentation visible?
Yes, yes, sir. You can zoom it. You can full screen rather.
Full screen.
Yes, yes.
Yeah, it's in full screen mode.
Yes, yes, yes.
Yeah. Thank you. Thank you so very much for this coordination, Dr. Rinko. Yeah, so we'll be discussing a little bit about biochar today. Basically, what is biochar? I mean, this is an interesting question that keeps popping up every now and then. If we really look at any of the phytomass that is available, maybe I can restrict it to on this planet. Maybe I don't need to dig deep into the definition of phytomass with you all coming from an agricultural background. Basically, any product of photosynthesis is what we generally define it as phytomass. What happens in the course of photosynthesis is the carbon dioxide from the atmosphere is actually picked up by these green plants, and then it is embedded in the form of fixed carbon, which is basically solid carbon. And what we get is a CHO complex. That's what exactly is our biomass. Of course, it requires nutrients, and it requires water, it requires sunlight, so on and so forth. But fixing specifically in regards to, or talking specifically in regards to CO2, the photosynthesis process takes in carbon dioxide from the atmosphere and then fixes it in the form of a CHO complex. Now, the CHO complex on a stoichiometry basis has got a chemical formula of C1H1.4 and O.6. C1H1.4 O.6. This is what exactly is the broad chemical formula or chemical structure of biomass. Now, this biomass, when we heat it under controlled environment, it leads to disintegration of this CHO structure, resulting in carbon content of typically more than 70% being present in the final or end product. Now, that is what we very broadly define as biochar. So, take any biomass, heat it under certain control conditions, and what is the end product is basically biochar. It is biochar. It is different from coal in the sense that coal is a long-term product, millions of years of similar kind of cooking activity that nature does for us free of cost, whereas biochar is something that we synthesize it artificially by heating biomass under certain control conditions. Now, what is this composition of biochar? Typically, when we talk of composition of biochar, somewhere between 60 to 90% by mass is carbon, between 5 to 30% is oxygen, 1 to 6% is hydrogen, and balance are certain notional compounds, and of course the ash, which is the mineral content. So this is the broad distribution of biochar. I'm going to the next slide, please. When we really look at the proximate analysis is basically the analysis wherein we try to understand how much is the carbon or how much is the fixed carbon, how much is the moisture, how much is the volatile content in the final product. It need not be biochar, in any final product. When we look at this kind of distribution, that is what is called. Like to draw your attention to the fixed carbon component, maybe pointer. Yes. So I draw your attention to this particular column, please, where we are talking of fixed carbon. So here you can see it's always above 70-75%, except for this particular field. So when we really look at any of the typical biomass, then we increase the carbon content that is originally present in biomass to the extent of 20%, around 20%, to something which is more than 90%. So the synthesis of biochar is the process wherein we increase the carbon content of the biomass from somewhere 20-ish in mass percentage all the way up to about 70 plus or minus 10%. So this is what is important in terms of the definition of biochar. And this is the ultimate analysis data wherein we are looking at the CHNO composition for the biomass itself, for the biochar itself, I'm sorry, and the ash which is remaining. So this particular table is basically laying out or is exactly quantifying the CHNSO compounds in the biochar as well as in the ash. Now, what is very interesting is the calorific value. Okay, here the interesting part of the calorific value is always the calorific value is more than 24, 25 megajoules per kg. Now, if we really look at pure carbon, that is pure C, the calorific value is to the extent of about 30 megajoules per kg. So 30 megajoules per kg to about 25 25-ish megajoules per kg is what is the range in which the calorific value of this biochar varies. The essence of this particular statement is that this biochar can also be used as a source of energy. Whether that is the right way of using biochar, whether it is the right way of using biochar or not is a different question. But the sum and substance is biochar can also become a very good source of energy by pure means of this particular calorific value. Going to the methods of production, there are different methods in which or through which this biochar can be produced. One of the simplest and most well established or conventionally established process is through what we call as slow pyrolysis. Now, pyrolysis is a process wherein we heat biomass in absence of air. So you take a container, let us say you take a pressure cooker. In that you put biomass, you remove air, and let us say you put some inert media like nitrogen, and then start heating it. It is as simple as that. So heating of biomass in absence of air is the process of pyrolysis. It is as simple as that. Now, at what temperature do we carry out this pyrolysis process is what will dictate, and the rate at which we heat is what dictates something as slow pyrolysis or fast pyrolysis. Now, both the processes are similar in the sense that heating takes place in the absence of air. In case of fast pyrolysis, the rate at which we heat the biomass and the temperatures at which we heat them is different as compared to the slow pyrolysis. The end products are different. Basically, the portfolio of volatiles that are released in the process are different in slow pyrolysis and fast pyrolysis. And the quality and composition of the biochar that is produced at the end is also slightly different. So that is the most important aspect regarding pyrolysis. Now, one of the important challenges regarding this pyrolysis process is lot of volatiles are released in this process. So your feed is biomass, the required end product is biochar, but one unwanted component is released in the form of volatiles. And along with these volatiles, you also get moisture. So it is a mix of water and hydrocarbons, higher hydrocarbons. Now, this product is something which is a little unpleasant to handle. Okay, it is not impossible to handle. It is very much possible to handle, but it is a little unpleasant to handle. So what exactly happens is this particular product can be carcinogenic. I don't say it is, but it can be carcinogenic. It can contain ring structures and so on and so forth. So while pyrolysis is a process which can produce biochar, there is one more process called as gasification, which produces the same biochar in a much more environmentally benign manner. Now, in pyrolysis, we heat the biomass in complete absence of air, but in gasification, the same heating takes place, but in presence of a small quantity of air. Now, just to give you a benchmark in terms of numbers, for every kg of biomass, we require about 6 kilograms of air for complete burning. That is, burn the biomass and then release heat into the atmosphere. That is complete burning. However, pyrolysis is the process wherein you heat the biomass in complete absence of air. So one extreme is combustion where you give 6 kg of air. Another extreme is pyrolysis where you give 0 kilograms of air. Now, gasification is a process wherein you give about 1.5 kilograms of air for every kg of biomass. So you can see stoichiometrically we are giving only 1/4 the amount of air required for combustion. And in this particular course, what happens is conversion of biomass into biochar takes place through a process called as gasification, wherein biomass is slowly cooked with the heat being released internally. So in gasification, no external heat is required, but heat is released internally by partial combustion of the biomass. And because partial combustion of biomass takes place, the temperature within the gasification system remains at an elevated level, something like 1000 to 1200 degrees centigrade. Now at this particular temperature, the volatiles, whatever are released, they tend to break down into smaller hydrocarbons. So what happens in the process of gasification is we get biochar. We also get gas, which is very conducive to handle. We get a gas which is composed of components like hydrogen, carbon monoxide, methane, carbon dioxide, so on and so forth, rather than condensable hydrocarbons, that is C6 and above. So in gasification, we generate permanent gases rather than condensable hydrocarbons. Now this gas, whatever is generated, is very much amenable for being used in industrial burners or internal combustion engines, so on and so forth. So basically what I'm saying is, while pyrolysis is a well-established process for biochar generation, the new generation technology is more about gasification, wherein you generate biochar in a very benign way, and the gas that can be generated can be used for generation of heat or electricity. Now, this particular facility that I'm showing is a gasification system that is present in our campus at Indian Institute of Science. And this is rated for consuming 100 kilograms of biomass every hour, and it can produce almost 30 to 35 kilograms of biochar every hour. And in the course, it can generate concurrently about 60 to 65 kilowatt hour of electrical energy, or it can generate 150 kilowatt hour of thermal energy. Now, this is a gasification system which is available in Indian Institute of Science. I extend an invitation to all the participants at UAS to come and visit this particular facility. I can put it in operations. Now, this particular facility has got one additional advantage in the sense that it is already rigged with the downstream cleaning and cooling process. Now, here on the left side is the reactor. Biomass goes from the top, air goes from the sides, and char is extracted from the bottom. Gas is extracted from the right side, and this gas can be used for variety of end-use applications. Now, the beauty about this particular technology is this particular technology, by means of making small changes to operating condition, can be used to maximize generation of biochar and minimize generation of gas, or it can be tuned to maximize generation of gas and minimize generation of biochar. So here you can see in one particular case, I am representing about 4 kg of biochar per hour. It consumes 100 kg of biomass. It can generate 4 kg of biochar. In this case, it can generate 100 kilowatt hour of electrical energy or 300 kilowatt hour of thermal energy. In another extreme, the same facility can take in 100 kg of biomass, can generate 30 kg of biochar, while producing either 60 kilowatt hour of electricity or 150 kilowatt hour of thermal energy. So this is a plant which can be tuned to end use requirements. So that is the beauty of this particular product. Now, insofar as the end use of biochar is concerned, would not like to spend much or dwell much on this because it's a well-established philosophy. The simplest use of biochar is for soil amendment. We make use of biochar, a lot of biochar we make use of for actually removing phenolic compounds from water. And today, the most important utility of biochar is in carbon sequestration. Every kilogram of biochar, which contains, let us say, 90% of fixed carbon, is equivalent to almost 1.5 kilograms of carbon dioxide that is sequestered. So that is where the utility of this biochar is. And here you can see the carbon sequestration potential. 1 ton of biochar can lock away about 2.5 to 3 tons of carbon dioxide equivalent. So That is the most important philosophy here. Today, a lot of data centers, today, a lot of electricity guzzling facilities are actually buying this biochar so that they can offset their own carbon footprint. Cost of biochar in carbon trading, here you can see 1 ton of biochar is trading anywhere between $250 to $900. So this is becoming a reasonably good business opportunity. Potential for biochar generation in India. Today, India is generating almost 750 to 800 million metric ton of agro residue. Out of this, about 500 to 600 million metric ton is used for use as fodder or any other alternate applications. So we have another 200 million metric tons of surplus residue that is available. Out of this, 60 metric tons of biochar can be synthesized per year. That means somewhere about 150 to 180 metric tons of carbon dioxide sequestration can be claimed through this carbon trading. Similarly, we can arrive at the biochar potential that is available across the globe. And what are the best feedstocks which can be used for synthesizing this biochar? So here you can see one is typical woody biomass like forest residue, coconut shell, so on, so forth. It can be subjected to high temperature pyrolysis. We get very stable biochar. We get biochar which is of very high quality. It has got high surface area and so on, so forth. The other one is typically herbaceous material, all our conventional agro waste. Now, this also synthesizes biochar at relatively lower temperatures, but this is very rich in nutrients. So, the moment we put it back in soil, it can substantially displace artificial nutrients through fertilizers. So, due to the paucity of time, I would like to close my discussions here. Maybe I have another couple of minutes for taking any quick questions, please. Thank you so very much.
Thank you so much, Dr. Anand, for giving your time. I know your hectic schedule, and you came and gave a very important topic, depending on the quality of biochar and at what temperature it would be, and how different units we have, gasifiers, pyrolysis, and other technologies, and how we need to adopt them with reference to the climate issues now. So I thank you on behalf of the University of Agriculture Sciences, our scientists who are seated here, our faculty members and entrepreneurs. So anyone who has any questions, you're free to ask. You can come here directly and just, you can ask Dr. Anand. Please come. Yeah, we have a young entrepreneur who's going to come and just ask you. So,
please. Please.
Yeah.
Hi, Doctor.
Namaste. Namaste.
Yeah, namaste. That was a very insightful presentation. I just have a quick question with regards to the biomass which you mentioned, which can be used. Is there any opportunity that we can mix, multiple feedstocks during the process of biochar, or there is a particular way that we have to use just, one type of feedstock?
I must say, it's a very important and a technically relevant question. See, we can go ahead and then mix any type of biomass, because broadly any type of biomass qualifies as a CXHYOZ complex. Now, insofar as gasification is concerned, the only criteria is you take any mix of biomass, as many types of biomass as you want, but it has to be densified into pellet or briquette form, having certain particle density and bulk density. Other than that, there are no other restrictions. Any type of biomass can be mixed. So some and substances, loose biomass cannot be used in this gasification process. It has to be densified, please.
Okay. Yeah. Thank you so much, Doctor.
Thank you.
Any other questions? You can come here, Panama, and you can ask, because it will not be, he cannot hear from there. Yeah, please ask louder so everyone in the house can hear.
Hello, sir.
Namaste.
Namaste. You said about different processes for biochar production. So I'd like to ask you, which is the most cost-efficient way of producing biochar, which is technically feasible also?
It's a very good question. Again, I must compliment you for that question. See, there are two things. One is whether I'm looking at it purely from a scientific process point of view. or whether I'm looking at it from economic perspective also. So we need to look at what is called as the net energy ratio. Net energy ratio is the amount of energy that you spend in order to produce some product. Okay. Now, when we are looking at this particular thing, there are two processes. One is pyrolysis, the other one is gasification. In case of pyrolysis, you have to produce heat from outside source. External heat has to be produced, but the biochar quantity that is generated is more. So if you have some external source of waste heat available, then you can go for pyrolysis process. However, if external source of heat is not available, then gasification would be the ideal route of production. In this case, the quantity of biochar available is a little less, but you don't have to spend money on any external source of energy. So it is a techno-economic question, please.
Okay, sir. Sir, specifically, I would like to ask you about coffee waste biochar. Can you throw some light on it? How it
See,
can be
yes,
technically
coffee
feasible?
waste biochar can definitely be taken through the process of gasification. Only limitation would be if you can convert it into briquette. Then our own experience, we have done a little bit of work with Tata Coffee and other groups, wherein the coffee waste is actually very rich in volatiles. So if you can synthesize it in the form of a briquette, then we can simultaneously generate almost 25 kilograms of biochar while also generating electricity for the estate in and around. So coffee husk and coffee char is a very good feed for this particular process.
Okay. So can you throw a bit light on artisan level kilns, which it is trending these days? I'm just curious whether it is profitable or not. Artisan level pyrolysis units.
For me, more than profitability, there the challenge is regarding the environmental aspects.
Okay.
So today, because of the stringent form of environmental aspects, these artisan level biochar formation processes can get a little challenging. And the challenge also comes from the point of view that whenever you synthesize any biochar, you will have to get it certified through some third party medium. Now there, if the environmental conditions are not really taken care of, then it may become a challenge.
Okay. Thank you so much.
Thank you.
Any other faculty members, scientists, or any entrepreneurs or research scientists? Any questions from the house? Feel free because they're from all the and they are meeting us. We are from very far. Very nice. Please take one picture. Please take one picture and send it. Yes. Anyone here? Anyone behind? Any other? Ma'am, Kamla, Dr. Kamla Bhai, any question? Dr. Darshan, any questions? Dr. Gayatri, any questions? Any other scientists? Dr. Sringesh? Okay, Dr. Sir, you have any questions? Entrepreneur, sir? Yeah. Okay. Okay. One of the entrepreneur is asking me to ask you, what is the importance or the use of bamboo biochar? Because now bamboo is a blooming biochar industry and he wants to know, yes. And one more is Prosopis juliflora, which we call in Kannada Bellari Jali. So these, that yes. One, bamboo and this one, Bellari Jali, they are asking, what do you feel about using these as for producing biochar, the biomass?
Perfect. Again, I must say both of them are very good questions.
Question? Yeah. Okay. So, doctor, continue. Then after one more question. Okay.
Yeah. See, when it comes to bamboo is potentially one of the best biomass feeds that can go into this biochar synthesis process. The reason being, the biochar that is produced using bamboo has got exceedingly good surface area. Okay, the total surface area per unit mass is exceedingly high for bamboo based biomass, especially the bamboo that is a particular variety called as Bima bamboo that has got very high surface area. Now the moment surface area of biochar increases, the best part here is the economic value for that shoots up. Okay, because the biochar derived from bamboo can be used for filtration purpose. can be used in toothpaste, can be used in pharmaceutical industry. So the terminal use of biochar from bamboo is very high because of the higher surface area. We can get as high as 900 to 1200 meter square per gram. Whereas the quality from mixed biomass like briquettes, so on and so forth, is a little low. So yes, bamboo is a very good source for biochar synthesis. The other thing is the quality of gas generated from bamboo gasification is very high. So simultaneous generation of heat as well as electricity is possible. That is as far as bamboo is concerned. As far as juliflora is concerned, there also the quantity of biochar generated can be very high, while simultaneously giving good quality of producer gas. The surface area there will be a little low, somewhere in the range of 600 to 700. A little bit of post processing, and then it can be used for a variety of end use applications, mostly these high end end uses. So it can automatically qualify for biochar through European Biochar Association definition, or it can be sold for any terminal end use. One of the very important end uses, very surprising, a very funny end uses is we can actually convert this biochar into blocks and then sell it to the Gulf for premium. They use it in their hookah. So it sells at 250 to 300 kg per hour, 300 rupees per kg. So that is also one very important.
You can send it to the Gulf.
economic
Huh?
value.
You can prepare biochar and send it to Gulf. You'll get more amount.
Yes. You can. Actually, Indonesia has got a very good biochar synthesis facility, and their entire trade is to Gulf and for Turkey. I mean, wherever these people use a lot of hookahs, that is a economic advantage for them.
Yeah, wonderful, very nice. So I think it addresses both Prosopis juliflora bellarii as well as bamboo, and you can use these for biochar production. Madam, Dr. Kamlabai had one question. If you can come here and can ask.
Maybe I can take one more question, please. I need to
one more.
rush.
This is the last question. This is the last question. Yes.
Sir, good morning. I'm Dr. Kamla. Namaste.
Namaste.
Sir, usually in coffee processing, you have two types of processing, wet processing and dry processing. So which processing will be fit for this biochar production?
Madam, when it comes to coffee processing, see, for me, when it is the biochar synthesis process, it is a thermochemical process. So the feed should contain moisture less than 10%. So in any of the upstream process ensures that the moisture in the feed that goes into the gasification is less than 10%. That is okay for me. So I believe dry process gives that. But if wet process is something which is mandatory, then we can make use of low grade waste heat available, maybe even from engines or so on and so forth, to remove the moisture. Or even we can make use of solar energy for driving away the moisture. So for us, the briquette should contain moisture less than 10%. That is the only criteria, please.
Have you worked with either wet processing or coffee, this thing, sir? Have you worked with wet processing or dry processing?
No, we have not really worked on the processing side. We have worked on the gasification side. So for us, the incoming feed, we ensure that the moisture content is less than 10%. We don't really look at. Yes, please.
Because in wet processing, I doubt you get less than 10% of the moisture, because it only have a lot of pulp, and that is rich in lignin content will be there. In the dry processing, okay, that parchment you can, I think so that you can work out ideally.
Yes. So whenever we get wet biomass like this, like pulp. See, for example, we have got a lot of biodigestate, the waste from biodigester. We get that, we dry it, we convert it into briquette, and then we use it in the gasification. Now there the moisture content is as high as 47-48%. So there is no problem with moisture content. Once it is, we receive the material as is, take it through drying process to bring the moisture content to less than 10%, please.
Okay, sir. Because I worked in coffee board, and you know that there's a huge area in a coffee, the processing, you know that you get huge amount of this processing waste. So I just want, I'll just come and discuss with you personally, sir. So
sure, madam. Anytime you can coordinate with Dr. Inko, and then maybe as a team you can come to IIC. I will show the system in operation also.
Okay, fine, sir. Thank you.
Thank you so very much. Thank you.
Thank you very much, sir, for your time.
Thank you.
On behalf once again of the University of Agriculture Science, the PG Dean Directorate, the DR, and all our faculty members. I thank you wholeheartedly, and your values, your suggestions are always very important to us, and you are in association with us. So once again, I thank you on behalf of all and everyone here, offline and online. Thank you so much, sir. Thank you.
Thank you
Namaste.
so very much. Thanks all the members there for giving me an audience. Namaste and have a great time ahead. Thank you. Bye-bye.
Thank you so much, sir. Bye-bye. Thank you. So now you would like to speak? Come. We have our next speaker. I just give him just 10, 20 minutes quickly because then I'll have one presentation. So we have Sumuk K. Bhatt. He's a young dynamic entrepreneur and he's 20-year-old mechanical engineer with a passion for addressing social challenges through innovative solutions. With a solid foundation in design and analysis from his time at Bell Helicopters, where he specialized in design and analysis of rotor components, Sumukha has embraced the philosophy that waste is a design flaw. This belief drives his current venture, Null Waste Industries. Actually, he's the owner of that Null Waste Industries, a startup focused on transforming biomass waste such as coconut shell, mango, kernels, rice husk, etc., into high value materials like biochar, biopesticides, because he has worked on bio oil. We will listen from him about that, bioresins, and biogas. Through his leadership, he has successfully developed a cutting edge process to maximize the value extracted from the biomass waste, demonstrating his commitments to sustainability and environmental stewardship. So immediately now we'll put the thing for you. We will share his slides and we will just listen to him because he's already working with the industry. So just a minute, I will share the slides. Yeah, I have it. We have it. I have already taken it. You will get it. I think first we have to open it, then only 1 minute. I'll just open it and share it like that. This is yours, no? Pyrolysis, first one. Okay. Done? 1 minute, 1 minute. I'll just put it on the, our viewers can see. Just a minute. Is this the one, Biochar conference? Okay. So I hope everyone can view the slides. Okay. I will help in, yes. You will do it yourself or shall I help you? You can do it? Okay. Okay, go ahead. Just 10, 15 minutes.
Yeah, I sent you the presentation as well. Isn't that not a problem?
No, this was the one.
Okay.
Yeah.
I'll scroll it. Afternoon, everyone. I think introduction of the pyrolysis and what happens is done anyway. So all of you know about.
You I will help you. You can. The viewers will not be able to hear, so you have to be very close while when you speak.
Close to.
When you stand here, and because they will able to listen. If you can't
Okay.
hear, no?
Okay. No, not a problem. So I guess about how, because I have limited time, I'll skip through the part about biomass pyrolysis. I guess everyone knows about this. But in brief, during the process of pyrolysis, you get there are three outputs: solid, liquid, and the gas. Solid is what we are talking about mainly here is biochar. Various use cases. Bio oil is the liquid derivative that you get. It has various use cases as well, and finally you get biogas. So I guess previous Anand, Dr. Anand also spoke about types of pyrolysis. In brief, there are three: slow, fast, and flash. Based on what your main output that you're looking at, whether it's the solid output, which is biochar, you would look at slow pyrolysis. Most reactors that operate today on a commercial scale are either slow pyrolysis reactors, which mainly target for the biochar, or it's fast pyrolysis, which mainly target oil. And mainly as fast pyrolysis is used in not biomass pyrolysis, but plastic or tire pyrolysis it's used. And these are all high capital, high capex industries, bio oil and biogas related. So I'll mostly be talking about what we do exactly at our facility here at Null Waste Industries. We mainly work with coconut shell because uh, of its availability throughout the year. No problem with availability, first thing. And second thing is coconut shell already has we started this 4 5 years ago when biochar was not it was not a buzzword like how it is now. No one knew about biochar and its use case and all that. So coconut shell already has a set market in terms of its charcoal. That is a solid product. Coconut shell charcoal is used for activation and used as activated charcoal. So we started off with coconut shell. We still continue to do that on a daily basis. So what we have here at our facility here in Bangalore is a continuous process which operates at around 300 kg per hour of input coconut shells. Our operating temperature is around 650. I put 550 here just as an average, but 650 degrees is what we operate at. The continuous process, 24 hours it runs. And the product yield, um, because I'm an entrepreneur, I put all worst case scenarios here. Usually the bio oil yield is around 30 to 35%, but I put lesser because it would vary depending on biomass. For coconut shell, it is on the higher side. Biochar on an average, you get 30. Again, we do slow pyrolysis here at our facility. So yield is generally in this range. And biogas is the rest. We almost get around 90% efficiency with around 10% moisture loss, which is in the coconut shell. So from a commercial perspective, mainly the input cost breakdown for a day, let us say we operate it for 24 hours a day. These are all relative costs. You need not take it as absolute because it will vary, but your margins and your this thing would remain the same regardless of the biomass that you use. So considering we operate our plant 24 hours, we consume about 7.2 tons of coconut shells a day. At around 16 rupees a kg, this would be around 1.15 lakhs. And labor, we would this is a our plant is mostly automated, completely automated. So we don't require much labor. We just require them for loading, unloading, and packing. So we have around 5 labors per shift, 12-hour shifts, and that would be around. All these costs are on the higher side as well, which you assume. Rent is around 2,000 per day. You don't require for a plant like this. You don't require much area as well because it's all vertically integrated more than horizontal area. Apart from that, heating source is mainly electricity. What we have here is a hybrid system. We have an electrical plus the gas that is generated during the process is recycled. So and also considering that usually semi-automatic plants or lower grade plants use or artisanal kilns like someone was talking about, they use firewood. So considering even that, what we use, I have put around 10,000. So total cost would be around 1.4 lakh per day. I'm talking about, I'll talk about that. Yes. So, so your input cost is around this, and what you'd be generating revenue with would only be the solid output and the oil output. Oil output because we created a market for it. So if you look at the solid output, which is biochar or coconut shell char, it would if if your input is around, if you buy it at around 16 per kg, the output you would get around 54 rupees a kg, which would generate around this much of revenue. It for a plant like this, biomass pyrolysis plant, your major revenue is from the solid source, which is biochar. And there are some thermal savings, but we don't consider that while calculating your cost analysis or ROI. But still, we get around 2.5 tons of biogas per day, and we have a facility where we store the gas and use it either for burning or uh, generating electricity. We have both at our plant here, we can generate both heat and electricity with the gas. So we do both. And major coming to the bio oil aspect of it, if you look at this, you see that 1,16,000 is what we get from the biochar, which is not enough to cover our total costs per day. So we are at like around 30,000 deficit. So if you don't cover that, then this whole cycle of trying biomass pyrolysis to make biochar doesn't make sense on an industrial scale. So we resorted to trying to commercialize the oil aspect of it, and it took us a couple of years to come up with the material. But what we did was, we'll have to, like how Professor John Bernard was saying, the oil doesn't have much use if it's just used like that as a raw material. You'll have to refine it for it to have some commercial use case. So what we noticed from especially coconut shell bio oil was that it had high phenolic content, around 20-21% was phenol and phenolic compounds. So we thought, okay, phenol is a major industrial chemical that is required, and majorly it's a petroleum derived chemical, doesn't have any bio alternative. So we thought, okay, probably we can make biophenol. So we started off. It's a simple fractional distillation method through which you can get the phenol rich part of the bio oil. So we did that. We have a distillation unit which will separate the phenol rich additive from the total bio oil material. From this, we get around 70% of that material is phenol rich. Rest base material is 30%. You get around, in the bio oil, mainly it is around 35 to 40% to around 60% is water basically. Rest are all the chemicals that you would use. So again, this phenol rich additive goes for various applications, industrial applications like plywood industry, foam industry, etc., which we supply to. And the base material as such is used in agriculture, that we supply to agriculture pesticide and bio based pesticide and insecticide manufacturing companies. They procure this from us. They make their own formulations for different use cases. So at this rate, we generate at around 34,000 to, in the worst case scenario, we generate around 34,000. In the best case would be around 43,000. So totaling that, if you look at in commercials and ROI analysis, our input would be, like I said, 1.4 lakhs. And with the sale of this, the oil aspect of it as phenol rich additive and base material, an approximate of around 1.5. So around 9,000 to 20,000 rupees of profit, including all costs concerned, you'd get around that much of profit every day. So ROI basis around 6.3 to 12.4% daily ROI. This would only make sense if as you scale this up, it would make more sense. This is at a scale that we are operating. This is more of a pilot scale, not a large industrial scale. But we operate it daily because because we could manage to get enough demand only for this amount of oil that we make as of now. So capital investment, machinery that we made, it was all self-fabricated, made here in Pina and other industrial areas, and we did it on ourselves. But approximately for a continuous plant of this scale, you would require around 50 to 60 lakhs to do it. And which would include your shed construction, your machinery, and power. This would be a semi-automated plant. It's not a completely automated plant. And usually biomass pyrolysis plants, unlike tire or plastic, would require stainless steel as a raw material, because these are very volatile vapors, not like tire or plastic vapors. So you will have to use SS. So the cost increases there. The capex increases. This is the capex that you are asking. So capex increases. Your capital expenditure would be around 50, 60 lakhs if you're starting off. I didn't invest that much because I did it from used materials. I started during COVID. So during that time, I had a lot of industries that shut down. So we got materials for scrap rate. So we managed. Yeah, I did it myself. We did it ourselves. We designed the whole thing, fabricated it in-house and opinion. We assembled it. I'm a mechanical engineer, so this is what I do. So making the machinery wasn't the problem. It was handling and running the running it continuously, because it's a continuous machinery. It shouldn't shut down after. Yes, it's a 24/7 operating process. So that is what would make sense if you're doing it on a commercial scale. A batch type process wouldn't make sense at all. It wouldn't make sense if you're doing let us say if you're making only biochar, probably would make sense, but scaling would be a problem. And most batch type units are wood fired. So by only biochar, if you're expecting only biochar, the only way to make it sustainable is through carbon credits currently. If you don't get carbon credits, your biochar unit on an industrial scale doesn't make sense. That is why still artisanal method where Contiki kiln, that is the only thing that is making sense here in India. There is no large scale biochar production that is actually working on a commercial scale, because if you concentrate only on biochar, uh, it doesn't make sense revenue wise unless you can capitalize on getting carbon credits. And carbon credit validation, we don't have our own standards. We have to comply with EBC standards, European Biochar Union standards, or IBI standards, international states. We don't have standards. So when we have to comply with their standards, they have stringent measures on which unit, like if you're fabricating your own machinery, then you have to go deep down into how the steel was processed and all that, which becomes a very cumbersome process. And no, even now for our unit, it's been around 6 to 8 months now. It's still going on the process of LCA, where they do analysis to give you the carbon credit certification. That will not happen. For it to happen. So future possibilities, what I wanted to most talk about, because our major thing in our industry is that for a large scale biochar production unit to work in India, you'll have to capitalize on the oil and the gas as well. Gas anyhow you can reuse it. Can also create. We also generate electricity. We don't give it back to the grid because our consumption is more than we have more consumption of electricity, so we don't give it back to the grid. But we have a 40 kVA gas generator through which we generate electricity for our plant. So the first 3 hours of our plant starting, we take it's in Mardi Road, Nice Road Junction, Bangalore. So
how much biochar you're producing on a daily basis?
Daily basis around 2 tons, 1.8 tons. Yeah.
How much workforce laborers?
We have 4 to 5 per shift now. So in the morning there will be 4 to 5 people, and then in the night there will be around this. We need them only to load and unload and pack. That is all. So oil is what we majorly worked on, because most people, the previous presenters also spoke about um, oil being a hassle in this process more than a revenue potential. But we saw it differently, because without making use of that oil that comes out, it doesn't make commercial sense, and you cannot scale this process at all. Because gasification might work, but at the current rates that the government buys back electricity at, if you're putting up a gasifier unit like Dr. Anand spoke about, you get 60 kilowatt of energy per whatever he said. 60 kilowatt of energy, government buys it at around close to 2 rupees. It doesn't make sense for you at all, because your raw material price, your landed cost of you said briquettes, not a briquette to run it in a gasifier. Any briquette landed cost currently would be around 10 rupees a kg. So it doesn't make sense. And your biochar also, you cannot sell it for more than 10 rupees a kg. For a farmer, it doesn't make sense for put an input where I given some biochar and they say it is around 50 rupees a kg. It doesn't make sense. It's not a high value material, biochar. So if you put a gasification unit, the revenue won't make sense at all. Because both products that you get, biochar and electricity, are very low margin, low value products. So only way to scale up biochar, scaling up a biochar manufacturing unit in an industrial scale, we have to make use of the oil as well. Oil has a lot of applications in agriculture. Same specification given West Harvard years ago. Currently in Harvard, they're using 5 to 6 times oil in this biomass that we have extracted. There are PhD projects going on there now with different oils that we have given.
If your unit reports the amount of oil you produce, because in our unit only we are getting 12 to 15% of oil.
We get around 35% oil. It's a continuous process, so
yeah.
It doesn't matter. Even if it's a batch type process, you get around the same yield. The only way you can increase yield of oil is to increase the rate of heating. The faster the rate of heating, higher the oil output. You cannot go off. But 12 to 15% is really low. Depends on your biomass as well. Probably the biomass that you have higher the lignin content and cellulose content, you get more oil. So it depends on the biomass. Probably if you try to coconut shell, you must get around 30%. It's not some locations. Probably you don't have we have 3 condensers. So have 3 condensers in the system, and then you will have maximum oil. Your mass balance would be the same. If you put 100 kgs of biscuit, you are not getting the 30% oil. If you're getting only 12 to 15% oil, the other 15% would have to be gas or something else. The mass balance will always be the same. So, industrial applications, the application that the resin industry is supplied to, that is plywood, it is used for. Foam industry also it is used for. That mattresses and other foam manufacturing industries.
The oil.
Yes, oil use cases.
We are having bio oil as one of the products. So not many people have done a lot of research on bio oil. Biochar, I think already using, but bio oil, is already its industry. Probably they are working. Main concentration is on the bio oil.
Yes.
So that's why he's telling which industries are buying the bio oil and how we can.
Biofuel industry is one problem because, like Professor John Bernard was saying, because biomass has oxygen content. Bio oil really high water content. It doesn't have a flash point or it doesn't have a calorific value. As such, we have to remove the water. We do vacuum distillation, remove the water content, and then we can use it as fuel. But it's a very low value. Usually mixed with tire pyrolysis and plastic pyrolysis.
They are very good.
It works for the oil is what they extract. They get 5 to 6% carbon. Cannot be used for biochar. It goes for these dyeing industries and other things. Agriculture also IHR, CCRI, Central Crop Research Institute, Central Plantation Crop Research Institute. Recently, IHR, 2 years back, they tried it with grade. They tried it with grades. Recently, it access very good fungicide. So we tried targeting. My data is a matter. Our major crop is areca. There is 2 crop diseases that are needed, which is from a fungus, Phytophthora palmivora. So major fungicide that is most resistant fungicide is boredom cell. We replace that for the major cross disease, which is coffee, areca and grapes. And from the last 2 years, it's been working with all the model farms that we replaced this boredom cell. So we replaced this boredom mixture with this oil that we have refined oil, and it's working well for areca nut and also coffee. Central Coffee Research Institute recently also they took around 100 liters of this oil because they're doing some research there. It's in Seawood, near Hungary or something. So they are
biopesticide, fungicide.
So you can add one more bio now.
Yes.
If the 3 bios you already have.
Bio oil covers most of this thing, and this resin application is actually plywood manufacturing. They use all harmful chemicals. No one knows about this, but formaldehyde is a major chemical that is used. It's a carcinogen. So what we noticed was when we use this oil we could use this oil firstly in making the resins used in the plywood industry, and when the oil was used, it somehow mitigated the emission of these formaldehydes, which was a major thing. So now we supply to these resin industries, plywood industries who make these resins. Good amount in this, this industry at scale. Usually it is a low margin, high volume industry. But for us it works because your biochar, if it sells, it covers 80 to 90% of the cost. So even with the 20 to 30% margin in your oil, you can make good amount of money if you operate it at scale. Currently, we make around 2 tons of biochar. We make almost the same quantity of oil per day. So we have enough market we have established only for that quantity. Even if I want to scale up now, I cannot because there's not enough customers for the oil as of now. Awareness is not there, but it is coming now, especially for other industries. We are trying anyway. Industry is easier to accept. Agriculture, a lot of research has to be done before it can actually come into use. So fungicidal application, this is the report that I got from CPCRI as a report. So they tried it at 1:2. We compared this with what is currently used, which is the boron mixture, copper sulfate lime mixture. At the same concentration, if it works, then it will make commercial sense. Even though the cost, I think farmers there that we interacted with, they said per barrel cost them 800 rupees or something per barrel, 200-liter barrel, then it's copper sulfate and lime. Our solution would cost them half the cost. It would be around 300 to 400 rupees a barrel. And it had almost the same effectiveness. The concentration at 1% concentration is 1 liter to 100 liters of water. So our oil, when diluted in 1:100, also worked really well for this fungus. This was a lab trial. This was at bioassay or something that they got, and this was 2 years ago. Now they can actually give a certificate. This is a biotech plant that we first started off with. My presentation will have to. I have mailed you my presentation. If you can open it, I'll run this video.
Is it there? Okay, but
yeah, it is there in your Yahoo mail.
Oh, Yahoo Mail. Oh, you sent it in Yahoo Mail.
You sent me that mail ID.
Okay.
That is just a video of the plant.
Okay, one minute. Let me check here. Can you send it on Gmail? If you can send it, it's easy. I don't remember the password. Gmail password, I can immediately put.
Okay.
You send on Gmail. Same thing you send on Gmail. I think we should visit your plant once. You just put it Gmail. This is the address. If you put it here, I'll open immediately. You see?
I'll send it to you on WhatsApp only then.
No, WhatsApp won't open here because it's already having a lot of things I have to delete. So
okay.
You from there to you send it to us. Rinku V2601 at gmail.com. At gmail.com. Just a minute. He will like to show you a PPT, so a presentation. of his company, video of his company. So I'm just connecting. Okay, did he send? Yeah. Send? Okay. Okay, in the meantime, you can just keep speaking. I just don't see the email now. That student is not there. Okay. Okay, okay. Panama, just 1 minute. Can you come? Can you just find out the email address of Dean Agree, write it at Dean PGS and just send one email for one printout. Just ask them, Dean PGS email. Okay. Fine. If it comes, then we will do it. You can continue, then we'll play. Okay. You can just continue here. Okay. We just share the slide then. Where is it? Just a minute. Has it come? Okay. Oh, where has it gone? Yeah, we were seeing here, no? Ah, here. Still not? Oh, is it? Inside. Because it'll come. Okay, so we'll share again because I think they are able to see anything there. Oh, this is all seen. Okay. Okay. Done. Wait, let me see where the share and screen and view. Okay. You had anything to send? Any other? That was the last slide. Okay. Thanks. Thank you. Okay. That one. Yeah. Can you bring one box there from outside? There's a box. Bring it in from there. Thank you. I'll just share it one more time. Yeah. So he has something to show you also, the samples of the biochar and the bio oil from his industry. You all can have a look. In the meantime, I will just quickly share my slide. You have any questions to ask Sumuka? You're most welcome. He's a very flourishing young entrepreneur and he's doing really well. So that's really nice actually. Yeah. You can put it here. You can put it on the table. You can put the table there. And you can show. So any questions for him? Any questions? Are everybody online able to view the slide? What I'm showing now? Can everyone see? Can you all let me know? Those who are online, can you see the PPT now? Impact of application of biochar to soil? Please let me know. Yeah, can you speak now and let me know if you're able to hear? Are you able to see the slides? Can you view the slides? Is it seen? Okay, fine. I'm not sure whether they are able to see, but anyway, please let me know. Okay, we quickly, any other questions for him? Shall I quickly start so that we can then go for lunch? Okay, so this is the last presentation for today. And after that, we'll have lunch and we'll see the unit running. Actually, it's already running. So quickly on the impact of application of biochar to soil. And if those who are interested to have the slides, let me know. Later, we will share all the slides. Whatever I'm having, you let me know. And by email, we can send it across to you. So impact of application of biochar to the soil. So it's a very important topic. We have been hearing from the morning the importance of application of biochar to the soil because of its various uses and its properties. From providing, place for nutrients, then improving the fertility of the soil and giving place for the microorganisms, etc. We already know what biochar is. It's a carbonaceous solid, and it comes from the Greek word, which is pyro, which is fire, and lysis is breakdown, which is known from the Greek word already. And you can do the pyrolysis anywhere between 300 degrees to 800 degrees, after which it will break down and it will turn into ash, because ash is different and biochar is different. We'll look into that also later. And if you want biochar, it's in the presence, in the absence of oxygen, I would say, or very, very limited oxygen. Rather, it's absence of oxygen. If you want to look, see how biochar looks in the microscope, you will see different feedstocks, different materials will have different pore spaces, and it all depends on the biomass. So that's how it's going to look. You will have macropores, you will have mesopores, and you'll have the macro. So there are different pore spaces which are seen depending on the type of biomass which is used. Now, if you look here, various importance of the biochar in terms of its physical properties, because that depends on the particle size of the biochar, its surface area, their pore size distribution, and surface heterogeneity and porosity. And then if you come to the chemical properties, ash, pH, hydrophobicity, toxic compounds, nutrient availability, functional groups which can be attached, aliphatic and volatile compounds. Then it increases what's the uses, enzyme activity, cell proliferation, cell viability, microbes, addition. That's why we say when we are putting the biochar into the soil, if we have microorganisms or if we don't directly put the biochar, because it will not have an impact, because it is not a fertilizer. If you see, it's not a fertilizer. This will stay in the soil for many years. Scientists claim from 100 years up to sometimes scientists say even 4,000 years, biochar will stay. And which type of biochar will stay? A biochar which is pyrolyzed at a very high temperature. 550, 600 degrees Celsius pyrolyzed biochar, which is obtained, will stay in the soil for a longer period of time compared to one which is at 300 or 350 degrees Celsius, which is seen in literature. Okay, then we come to its house for microbial habitats, microbial community structures, and protection against predators. So there's a place for the microorganisms to stay. One person was asking, as big as a football stadium, I can see a football stadium or a cricket stadium. If I think of a biochar particle, that large is the area, so many pore spaces, so many microorganisms can take their place for staying. And how much of carbon dioxide which can be sequestered? Because today, you see in Bangalore, we have so much of scope for having trees. Trees also the best sequesters compared to water, compared to the water part or the tree part. The trees are the best sequesters of the carbon dioxide. That's why we say afforestation, reforestation, growing more trees will help to combat climate change. But we are not doing that. And the second thing is now it is biochar, because biochar has the potential to take in sequester carbon dioxide. And the third is carbon storage and capture, which we don't do in India. That developed countries like Norway, United Kingdom, United States, and maybe other countries are doing carbon storage and capture, which takes and brings pipelines of carbon dioxide and pushes inside the rocks, which are, repositories to store these carbon dioxide gases for many, many years. But we should see which are the rocks which are feasible, and you should know better metrology and petrology for that, geology. And we suppose soil remediation, plant growth, nutrient uptake, and suitable agriculture. Then coming into the characteristics of biochar, it is very good for heavy metal remediation. So wherever you have that there is a heavy metal in the soil, you can apply biochar because it is good for heavy metal remediation. Then what we're talking from the morning on greenhouse gas emissions. So greenhouse gas emission mitigation, it is in the top list in these three which I mentioned to you: carbon storage capture, then biochar, and reforestation, afforestation, and then the sustainable technologies which we are using. Then improve physical properties. Because once it comes to the soil, then what all it can do, how all it, in which ways it can function. Then improved chemical properties as well, because you have cation exchange capacity also will be possible because you have cations in the anions. So therefore, we should see how best we can characterize, the characteristics of the biochar. So there, that's the very important thing which we have to keep in mind. Then coming to the impact of biochar on the soil. So once we add the biochar to the soil, what all it can do to us? It has porous space, so absorption will happen. It is low density. It has a very high surface area. And usually if you see a biochar is alkaline in nature, when you give it to an acidic soil, it will help. Otherwise, you mix it with the manure and you can neutralize the pH. Then it has mineral elements. It's rich in carbon and it has high content of aromatic structures and functional groups. So they're all correlated in one way: bulk density, porosity, water holding capacity, okay, and aggregates. Then you have the pH, then soluble organic carbon, then cation exchange capacity, CEC, and the nutrients. So therefore, for all these gases like methane, mainly carbon dioxide, and also nitrous oxide, there are many good things which the biochar has a very good role, which we will see in the coming slides. So microbial biomass is very important because it can stay. And one of the scientists from IHR had come down to see our unit. She was saying that even pathological, it has helped a lot in pest control. They have used larger dosage of biochar in their crops, and it is also acting as pest control. Okay, then we go to the next. If you see the role of biochar in improving the soil properties, nutrient retention and microbial activity. So we know biochar, it increases the soil pH. Also we know it's a complex clay organocomplex. And one best quality here is the slow release of the nutrients as per requirement. The plant will only take how much it requires. Even if you put more of NPK, the plant is not going to take. It will only take as much it requires. So this biochar will help in releasing of the nutrients. So nutrients are tightly packed, and whenever the plant wants, it slowly releases and it is taken away by the plants. So next season also, if it is there, then it is available for the plants. And then you see that it has a high carbon sequestration, which I already mentioned. Nutrients in microbial biomass enhanced and nutrients in organic food increased, because again you have nutrients. Where you have nutrients, you have the microbes, and when you have the microbes, friendly microbes, then they are useful to the environment. So you increase the population of the microbes as well. Then high surface charge and cation exchange capacity, I already told you. Why? Because it is a place which attracts. So once you have the nutrients, then you have all the charges, then they are available. You have many of them available. Then you have water holding capacity increase, and you have reduced bulk density. So therefore, leaching loss is also decreased. Then factors affecting biochar properties. So it all depends on the nature. So this is very, very important. On the feedstock you use, what kind of feedstock you're using? Are you using a woody feedstock? Are you using a directly green feedstock? So that will depend on the property of the biochar. Then you have rate of pyrolysis process and age of the biochar. Age of the biochar also is very important. Once you prepare a biochar, you cannot expose to the outside environment because it come in contact with water, it will come in contact with sunlight. So the quality will deteriorate. So what you have to do is you have to store the biochar as per the European Union standards. We have a book on the biochar. Those materials freshly prepared should be stored in a storeroom and covered with a cloth so that you don't expose heat to it and you get a quality. If you just leave it to the environment, what happens? It will absorb the moisture content and the quality will not be that great when you apply it to the soil. So all these things has to be taken care of. Okay, then we go to the next. Then you look into the way in which we are doing biochar properties based on pyrolytic temperature. If you see here, the temperature here is very high. If you see that the temperature is low, in a sense here the temperature may be 500, 600 or above nearly 800 degrees. If the temperature is very high, that means the heat is high, then you will see we have higher percentage of ash content, calcium, magnesium and potassium. You have a high pH, which we are already seeing. Also, we have fixed and aromatic carbon. C/N ratio is also high, and surface area. C/N ratio, always take care whenever you are putting something into, if you want a good C/N ratio, you have to take a biomass which is having a good C/N ratio. That means which has a very good calorific value. That is very, very important. If you take a biomass which is having low, then the quality will not be there in the biochar. Then it has lower volatiles and I already told you carbon exchange capacity. On the other hand, if you take a lower temperature, say 300 degrees Celsius, then if you see 300 degrees, it is just the reverse of this. What was high here becomes low. So you have ash content, calcium, magnesium, potassium, pH, aromatic carbon, C/N ratio, surface area will be lower compared to what was at a higher temperature, and you'll have the same. What was lower here, it becomes higher volatile content and CEC. So if you want a biochar, if you want that the students perform and get the best results, then the recommendation is we should go for a pyrolyzed biochar at more than 550 degrees Celsius and not lesser than that. Because that is the one which will remain in the soil for many years. And if you put with Dr. Lakshmipati's microorganisms, biopesticide, Azotobacter, Azospirillum, Rhizobium, Pseudomonas, whatever your things are there, give us also, then you will see that it will be very, very good in the coming years because it will stay in the soil for many, many years to come. We may not be there, but the biochar will be there. Then coming to the next, okay, I think I explained everything here. Then biochar properties based on feedstock. So you have to look into the feedstock. If you look into the woody biomass has a lower pH, lower ash content, lower NPK, calcium and magnesium, lower potential cation exchange capacity, lower exchange cations and higher total carbon. So this is the thing. But if you look into legumes, they are the reverse. In legumes, you see that it is a high pH, ash content also high calcium, NPK, calcium, magnesium, high potential of the cation exchange capacity. So these are the things. Everything depends on our feedstock. So therefore, we have an idea on the feedstock. Then we see what the next slide has to tell us. So biochar properties based on the rate of pyrolysis. Now, if you go rate on pyrolysis, just now Sumukha was talking about fast pyrolysis and slow pyrolysis. And this is a continuous fast pyrolysis, isn't it? Yours is a continuous slow pyrolysis. So if it is a slow pyrolysis, you have a higher surface area. If it is a fast pyrolysis, you have a lower surface area. Then age of the biochar, age, more oxidized group, more higher CEC, that is cation exchange capacity, and AEC. And then you can see the fresh biochar, less oxidized groups, low CEC and low AC. So these are all the things one should have an idea. And in a nutshell, if you look, biochar application increases soil, ash content and soluble basic elements, calcium, magnesium, sodium, potassium, etc. So therefore, we'll see that the electrical conductivity of the soil also will be enhanced. Now, with the application of biochar, we will see CEC, high surface area, high charged density on the biochar surface, which we just talked about. Then organic carbon is very, very important, recalcitrant and less mineralization. Total nitrogen increases the organic content. Then C by N ratio increases with the application of the biochar. Then you have phosphorus increases, abundant soluble phosphorus was forming during the pyrolysis process. Potassium usually was preserved and converted to potassium salts during the production of biochar and are soluble. Basic cations, higher base cations and high CCE. Micronutrient, that's acidic biochar, increases the availability. So if you see the applications to the morning lectures which we are industry, young entrepreneur, we know that biochar is maybe one is we say agriculture, then we say next carbon sequestration. You have electrode material, biorefineries, catalyst, wastewater treatment plant, soil amendments, adsorbents, and then you also have used in fences and in mobile and so many other applications we have them. Then we have applications of activated biochar, soil remediation, water treatment, catalyst activators, and super capacitors and fuel cells. So there are so many, I'm not going to details, but at least it gives us in a nutshell that there are so many uses we are in agriculture using, because today we want to sequester the carbon dioxide, which is a very major climate change issue for us at the moment. And we see that today in Bangalore, as compared to the former years, we are changing our climatic patterns. We are seeing extreme cold in the winters, and 1 or 2 months are that cold that we didn't experience 4 or 5 years back. All these years back, you didn't even require a fan, you didn't require a cooler, you didn't require an AC. But today, when you go out, you feel your car should have a AC, and your houses should run completely fan or whatever. So I think it's high time for us to see where all we can start using biochar, either in remediation or in wastewater treatment, because it has ample uses. Now, we have already talked about the application, how pyrolysis helps in producing biochar, syngas, and bio oil. That is the pyrolytic oil from the biomass. And here, I would like to mention, when you want to run a biomass, as Sumuk said, we need 100% dry biomass. We should not go for biomass which is even 0.5% wet. Why am I saying this is? This will hinder the production of the biochar. You will not get 100% production. You may have, some percent burnt, some percent non-burnt. So always when you want to produce the biochar, 100% the biomass should be dry. You should have enough biomass. Otherwise, if you are not using biomass, you will consume a lot of electricity. So, Maka, what have you used? You are using electricity or biomass to run your pyrolysis? The heat source. Electricity. You are using electricity? Okay. We here use the biomass. So now this is what we, from the DSC project, we try to, you can have a look when you come over there in the afternoon. We have 3 combustion units, and we put the waste into it, which heat up the pyrolytic chamber over here. So we have 2 pyrolytic chamber, and both have the capacity of 0.5 ton. Depending on the type of biomass, you can fill in rice straw, rice husk. We cannot fill in more because of the material volume. Okay, so only 100 we can fill 200. But if it is the coconut, you can fill more. If it's some other material, you can fill more. Then we have a blower. We don't have to use the blower. Blower is used when we have a wet biomass inside put, so that you can take off the air. Then we have another blower here because we have to give oxygen for running all these 3 units. When you come to the afternoon, you come to the field, you will see it in operation. And then we have a condensation unit over here because the oil is to be collected. And then when the syngas is produced, it comes through the condensation unit, and then cleans, and then it comes here and it starts burning. We have a very good syngas which burns. We are not burning anything. The gas which is heated up, the syngas which is coming, is burned. If I want, I can also tap it, and I can use it for some other purpose. That can be the hydrogen gas. For the next generation fuel will be the hydrogen gas. And then we have the biochar, which will be removed. You have to take out from here, and you can take out the biochar. From my unit, if I take in 100%, we'll have 15% of oil. Then we have 57% of syngas, and the remaining is the biochar. So this is what we are getting. 35 to 40% we are getting biochar, 15 to 12 to 15% bio oil, and the remaining is the syngas. Okay. So you can see when it was installed, it was 5-ton capacity. It's a 5-ton capacity. It came all the way from Pune. And we had only told the industry to put the gasifiers, the combustion unit. Otherwise, we had to spend per run 8 to 9,000 rupees on electricity. You can see when it starts catching fire, see the syngas. So that this pipe comes, it's connected, and you can see the syngas. Already heat is over here, the syngas. It also takes in flames. When you work here, you have to be very careful. I will tell you how to do all those, very simple. Then you have an outlet for connecting the biochar. She just now told us it is a biopesticide, bioinsecticide. It's a wood vinegar if it is from the wood origin, and that is the pure biochar. And it is called as the black gold. And for us, just adding biochar to the soil will not do good. Biochar, along with the organic amendments, vermicompost or any other thing, along with the microorganisms, will be the best. And then you can patent it. So we all work together and make a nice patent and give a mixture so that we can get a patent for our university. And this we had applied to the Fishbella grounds. And I would like to show you this slide here. We checked the organic carbon, okay? So these were the varieties for which we had done. And we saw the initial, this one, for biochar and vermicompost, because we took in the ratio of 1:3, because the soil already was devoid. You see there was very less organic content. That means you see it was only 0.5, 0.45, 0.31, 0.433. And after adding biochar, you can see there has been some increase. I mean, the analysis just shows us that there is an impact. What I want to try to bring out to you all is that if you use it in the right treatments and design and do it, probably we get in the coming years and months. Castor, sir, this is castor. Where is the castor? Castor, sir, I have another slide. Maybe you can take it from me. I have more NPK, other things also, because it was not from the beginning. When the plant was 1 month, then we have applied the biochar, but still there were some good results, and that cannot be really substantiated, but there has been progress. I will share with you, and you can see it later for me. We have for NPK, percent organic carbon, and then for other parameters which we have done. I have not put those slides. I can share with you. This is our unit. We'll see. This is the unit which we already shown. Yeah. Now, why I brought this slide is from speaking from a marketing point of view or the agricultural economics point of view, agriculture subsector, that is the greenhouse gas breakup from our agriculture sector is enteric fermentation of livestock, agricultural soils, paddy rice cultivation, manure management, crop residue burning, and others. So we will focus on this part, crop residue burning. So instead of burning a biomass, how much you see while burning, how much is going into the environment? 50 metric tons of carbon dioxide. And you see from other sources as well, from the agricultural soils. So where all the management can be taken care of. Then next, if you look here, I'm again concentrating types of agricultural carbon credits, which I was just talking and asking. So one is soil organic carbon, agroforestry, manure management, rice emission reduction, and here is biochar, which we are talking, and conservation of the agriculture. So if you apply biochar, then you can get for agriculture carbon credits for that. Then coming into the difference between ash and biochar, many people have asked me, what is the difference between an ash and a biochar? So we will quickly look into the slide. If you see ash, it's the product of burning, but biochar is not burning. The final product of carbonization. In the absence of oxygen, we are, heating. Then second is heating up or burning biomass with full open oxygen. But if you look there, biochar heating biomass is limited or no oxygen at all. It will be no oxygen. Then it has no permanent structure. It is anamorphic. But you see, biochar is a carbon structure. It is a proper carbon structure. Then you see it has nutrients like calcium, potassium, magnesium, etc. It can be said maybe as a fertilizer, but it is not here. It is not a nutrient. Biochar is not a nutrient. When you add the nutrients, when you add the organic amendments, when you add the chemicals, whatever, then it becomes a soil enhancer. It gives. So it's a material and you add, and it is available for the plant. So soil enhancer, but not a fertilizer. So you can, yeah. Soil amendment is the best. Correct, sir. You're right. So then we look another thing. As per the International Panel for Climate Change, they said that the potential of the biochar, that is to remove 2.6 billion tons of carbon dioxide. So you see how much the potential is. Today, people they are calling and they're asking me that in Bangalore we are not having many trees now. The way Bangalore has developed, the houses and concrete structure has come. Now, if you see agriculture universities like us and Indian Institute of Science, some green campus, some green lung spaces, military, little green. But otherwise, you see the roads are just the vehicles are going. Even in the midnight, we are seeing the people who are on the main highway. They have a lot of going to the airport or those people coming from that side. Coming to this part of Bangalore, they have to travel 2 hours to reach the airport. So till the metro is ready, then they have to take the vehicle. Now, how much of carbon dioxide emissions? How much of fuels we are using? One conference happened a decade ago, more than a decade ago, 15 years ago. What the scientists said, one fine day in 80, 90 years, we may exhaust petrol, we may not have diesel. Then what are we going to do? Do we wait for that day? Or now only decide what has to be done? Now is the time for us to think about, because time is tick is going very quickly and we have to take care. Otherwise, because of the climate issues, our farmers are impacted, our agricultural activities impacted, and all you scientists are working very hard. From the scientists, Dr. Anand and then Kamlavai and all the scientists, Dr. Lakshmipati, and all, I don't know your name, sir. I heard it as an entrepreneur. All, Dr. Anand, Pawan, and then from Chintamani, you come here. Okay, fine, so nice. Please also give me that. Take his name. So, yeah.
Slide there. Potential to remove 2.6 million tons of CO2. How much biochar we are producing?
Sir, it is that's what is the thing, no? Now, please, some of us just. Yeah.
Standard is even if you go to artisanal kiln, which is not an we are doing. Even if you go to an artisanal kiln, every ton of biochar you get it is considered as 2 tons of CO2 for every ton of biochar. So you require 1.3 billion tons of CO2 for biochar on an average basis.
Yeah, please tell once again, Sumuku. 1 ton of
standard is that for each for 1 ton of biochar produced, we know around tons of carbon dioxide.
Yeah.
So you would require 1.8 tons to remove 2.6. Okay, yeah. If you do it in a reactor like a reactor or what you have here, it is almost closer to 3. But if you do it in that artisanal kiln or pottery kiln, it's considered 2. That is, you get 2 carbon credits for every ton of biochar produced. 1 carbon credit is equal to 1 ton of CO2. So on an average, if you take 2, then you require 1.9 tons of biochar. Also depends on the so that approximately gives you can tell how much biochar we need to produce.
So therefore, sir,
and is it annually or
this is not said anything because I have taken this from the internet just to show the potential of the biochar, because this was main thing, so anyway. Yeah, there was one more thing which I wanted to show. I don't know whether it was there in the slides or I missed. All of you, please take your certificates. Don't forget, because once I write the names, I will get it signed from Dean PGS. There was one more. Yeah, here, if you see one more thing which is important is even reduces ammonia volatilization and reduces the nitrous oxide emission. So this is very important. Another feature where biochar is playing a very important role, which I forgot to tell you all. I just had not mentioned this. Reduces nitrous oxide emission because it absorbs. And then what happens? It is just like the ammonification. It converts nitrification, denitrification, and takes out the nitrogen. Like how you have the water treatment. Similar like that. Then you have the complete denitrification and finally nitrogen. So this is one thing. Okay. Pardon? Yeah, there is even Sir said correct. We have from the paddy fields also some amount of biochar, but I think some work needs to be done because there are fields which is rice grown without water. Now scientists are growing rice without water. So probably because here I think on one slide I have shown you from which all sources that this one is being emitted. Just yeah, if you see here, no? Paddy rice cultivation, 110 metric tons of carbon dioxide. And the maximum is entry fermentation and soil agriculture. And then you have others, deforestation and agroforestry. Crop residue burning is 50 and manure management. So that means to say, we should, when you have fresh manure and you don't take care of it and just keep on piling, then those gases are automatically going into the environment. Otherwise, if you run biogas, what happens after 11 days, you have carbon dioxide, then you have the methane, and then you have methane production. So you are having it. But here what happens? It's piled, and naturally it will go. Same in landfills also. Landfills also there is burning fire because they have all the waste. And then when it becomes anaerobic, then see any thing lit, then it catches fire. Otherwise, the gases are going, and we are sleeping, but the gases are going into the environment. So I think we can.
Agriculture contribution is 28% for GHC. Of course, you have given breakup, but compared to all sectors, agriculture is 28%.
Yes, yeah, because since we were only focusing on agriculture, I didn't put the others. Where we can try to do something, then it is good. So I think from today's talk, I'm sure we all will think of incorporating biochar in all the crops. All scientists today, you all added all your fertilizers as per POP and all that. You are a better expert than me. Take your suggestions.
Gas problem for time being.
That also will happen if Iran becomes very peaceful and then Israel and US will say, okay, because they have started it and tactfully and then,
They were given a very right time.
And the food also, I had to talk to two pastors. One said no cylinders, then others also said, and I said, please do it. So don't forget eating urde or and cancer. So anyway, so I think we all have to work together and do something because if you want to, because microbiologist also here is doing all the biopesticides and microorganisms, you have to have a consortium with the biochar and then the scientists will fix because later on, because this is a very short platform for me to even say how to what is the dosage of adding the biochar also. From 2 tons.
It's also for bio fertilizers. Collaborative.
So therefore, like we will include all these things. So any questions, anything, please.
Only laptop is doing it.
Yes, sir. Everything is a start. We are. How? Biochar particle size or soil particle size? Biochar ಅಂದ್ರೆ ಹೌದು ಬರುತ್ತೆ ಕರೆಕ್ಟ್. ಬೆಟರ್ ಇಫ್ ಯು ಹ್ಯಾವ್ 4 ಸ್ಪೇಸಸ್ ಪಾರ್ಟಿಕಲ್ ಸೈಜ್ ಎಲ್ಲ ಇದ್ರೆ ಒಳ್ಳೇದೇ, ಯಾಕಂದ್ರೆ ವಾಟರ್ ಹೋಲ್ಡಿಂಗ್ ಕೆಪಾಸಿಟಿ ಇನ್ಕ್ರೀಸ್ ಆಗುತ್ತೆ, ಮೈಕ್ರೋಬಿಯಲ್ ಸ್ಪೇಸ್ ಚೆನ್ನಾಗಿರುತ್ತೆ, ಅದರ ನ್ಯೂಟ್ರಿಯೆಂಟ್ ಅಕ್ಯುಮುಲೇಷನ್ ಚೆನ್ನಾಗಿರುತ್ತೆ, ಆಮೇಲೆ ಮೇನ್ ಇಂಪಾರ್ಟೆಂಟ್ ಕಾರ್ಬನ್ ಸಿಕ್ವೆಸ್ಟ್ರೇಷನ್ ಚೆನ್ನಾಗಿರುತ್ತೆ. ಸೊ ಅವಾಗ ಎಲ್ಲ ರಿಕ್ವೈರ್ಡ್ ಅದೇ ಬಯೋಚಾರಲ್ಲಿ ಎಲ್ಲ ಇರುತ್ತೆ, ನೀರು ಇರುತ್ತೆ, ಮತ್ತೆ ನ್ಯೂಟ್ರಿಯೆಂಟ್ಸ್ ಇರುತ್ತೆ, ಮೈಕ್ರೋ ಆರ್ಗ್ಯಾನಿಸಮ್ ಇರುತ್ತೆ. ದೆನ್ ಅವಾಗ ಏನೇನು ಆಹಾರ ಏನೇನು ವಾಟ್ ಎವರ್ ಇಸ್ ದ ರಿಕ್ವೈರ್ಮೆಂಟ್ ಗಿಡಕ್ಕೆ ಎಷ್ಟೆಷ್ಟು ಬೇಕೋ ಟೇಕಿಂಗ್. ಬಟ್ ವಿ ಶುಡ್ ನಾಟ್ ಫರ್ಗೆಟ್ ಆ ನ್ಯೂಟ್ರಿಯೆಂಟ್ಸ್ ರಿಕ್ವೈರ್ಮೆಂಟ್ಸ್ ಹಾಕ್ತಾ ಇರಬೇಕು. ಸುಮ್ಮನೆ ಬಯೋಚಾರ್ ಹಾಕಿ ಬಿಟ್ಬಿಟ್ರೆ ಅದು ಸಾಯಿಲ್ ಜೊತೆ ಎಲ್ಲ ಚೆನ್ನಾಗಾಗುತ್ತೆ, ಅದ್ರಲ್ಲಿ ಏನೂ ಆಗಲ್ಲ, ಬಿಕಾಸ್ ಇಟ್ಸ್ ನಾಟ್ ಹ್ಯಾವಿಂಗ್ ಸೋಡಿಯಂ ಕಾರ್ಬನೇಷನ್ ಮೆಟೀರಿಯಲ್ಸ್, ಇಟ್ ವಿಲ್ ನಾಟ್ ಡು ಎನಿಥಿಂಗ್. ನಾವು ಮಾಡಿದ್ವಿ ಜಸ್ಟ್ ಪುಟ್ಟಿಂಗ್ ಬಯೋಚಾರ್ ಹಾಕಿದ್ವಿ, ಬಟ್ ಅದು ಏನು So both you can do decent application also, and you can put it and you can mix it also. And andre many of the fertilizers, with the fertilizers, you can put it with that also. You can like immediately have the andre vermicompost jothe mix ಮಾಡಿ you keep it for 1 week 15 days, and ಅದಕ್ಕೆ ಆ ಟೈಮ್ ಅಲ್ಲಿ microorganisms. Standard recommendation actually the standard recommendation is not really come out. Scientists ಹೇಳ್ತಾರೆ have gone even more, but we are not having that much. But to tell you frankly, you can do it starting with 2 tons, do it with the organic amendments or whatever nutrients to this. Yeah, and then when you have more, then you can do it more, because of the more the better. And the more and higher the temperature of the biochar, 550 degrees ಅಂದ್ರೆ ಆ biochar purchase ಮಾಡಿ, ಯಾಕಂದ್ರೆ that will stay in your. How will you come to know? We university 600 is okay. Why you want to find out it? Even if it is 300 meters, they will get 500. He took the initiative 2 years. He did a study. We designed prototype and we assembled all the parametric parts. Only we will come to see your plant. So we did a result. You test what surface asking. How do you get to know? Yeah. Based on the report, C by N ratio we spoke about. Yeah, C by N ratio. That quality determined by that C by N ratio. If it's not, it doesn't go above 5. Quality biochar, C by N ratio. Quality biochar 500 degrees plus 50 degrees. C by N ratio is your quality indicator. Yes. C by N ratio is what will determine the rest of the biochar is actually biochar. Whether it is pure or just that standard qualified for credits, they look at C by N ratio. Okay. So that they'll tell you whether the biochar qualifies. C by N is everything you need to say by the way. Yes. You know, I think Dr. Anand said that ultimate analysis. Ultimate that C by N is C by N. Okay. Is most important. Yes. Yeah. Stability. C by N ratio. More carbon and less C by O ratio of the carbon by oxygen. Oxygen less is slow. And then it is not a standard. It is around 0.5. Before I forget, we all should take one picture or attend it here, so that this is only a beginning. I think we need. Yeah, right. 1 minute. Yes, tell me. Yeah, put this at FTI. FTI. Feel the on the 230. Okay, thank you. Yes, so. Okay, any other questions or anything? So, sir, tell me, sir. Yeah. No organic matter. Biochar, no, biochar, why biochar? No, I'll tell you. Biochar is the one which will help in carbon sequestration. Organic material is increasing the organic content of the soil. Manure, vermicompost, then you have farmyard manure, you have chicken manure, you have poultry manure, different kinds of manure. You have biomass manure also. There was one farmer in Garbada, now is no more. He never even threw a leaf out of his this one, his cleaner. And when we asked him why, he said that is the currency for me. What did he say? The leaf is a currency for me. That means that is a biomass which should go back to my soil. He didn't burn it also. He left it in nature so that it will compost on its own and go back, so that it will increase the organic carbon of the soil. Today we are depleted with the organic carbon. Now, if you are going to add biochar, what will happen? Biochar has those pore spaces. And if you add pore spaces also helping carbon sequestration, nutrient absorption, water holding capacity. So what happens? Overall, it gives you everything. It's like a cake which has all the materials. Then I separate either. I separate the other materials. They are all separated. Here I made baking powder, I put milk maid, I put maida, everything. And the cake is ready. So all the ingredients are there. It's like that. I don't know. So see, if you burn without a pyrolytic chamber, how much of emissions will happen? What's happening now? When you burn the agricultural stubble or the sugarcane waste or whatever, then you see how much of air pollution is happening.
On this part, I agree. I just want to do another process of that. What is your opinion?
I know she's also an environmental activist, but here being an environmentalist,
and what she was talking about, going to this,
see here, burning under controlled condition, we are not burning open oxygen. We are not, see, we are even another option. If you don't want to burn the biomass, you can use solar. Now we have solar panels. Put a solar panel above wherever you are having. Run your pyrolysis on solar panels. If you have wind energy, run your pyrolysis on wind energy. Because we have different areas in India which are good for renewable energies like solar energy, like in Rajasthan, in some parts of Karnataka, for all those solar panels. Then you have Nagarjuna near Tamil Nadu, near Nagarjuna, which is near Kanyakumari. Lot of wind farms are there. If you want to install a pyrolytic chamber over there, I would suggest if you don't want to burn biomass, use the solar, the wind energy to run your pyrolytic unit, and that is in the absence of oxygen, we are getting all the products. So here what I am showing you is you are not burning any biomass. If you are thinking on that angle, and I can substitute even for this. Because in some areas you have solar, some areas you have wind, some areas you have tidal, okay, some areas you have another kind of energy. See, today in Bangalore, many houses, 8 to 10 lakhs they are spending, and they're having a very good solar panel which will light the complete home. People have gone in, many Bangaloreans are about this. They're doing it. They are going away from the fossil fuel and going for the green energy, that is sun's energy directly. So like this, if we think, we can bring out such technologies where if you think I'm burning the coconut and all that, but here let me tell you, we are going to the when you come to our plant, per 10 minutes we are adding 6 kg of biomass. Per 10 minutes, 6 kg of biomass goes into the chamber. We add 850. That's why cheaper are now papers. We reduce it to 400 kg. This by some heat energy transfer, some efficiency. So like that, if we do, good. Otherwise, every human being has to plant one more tree in front. Is everyone ready? Every Bangalore you will say, I'll plant one more tree in front of my house. And how many, what is the population of Bangalore? Into that many trees. And then I say in Bangalore's time, in the next 10 years will be this, then we think about it. So these are something. Okay, any more questions? We break for the lunch.
All right, what comes next for you?
That was so nice. Please, photo session, please take your.
I'll take group photo after this. So, friends, I'm very happy to propose thanking because within a short time, Madam has arranged one of the innovative and interesting innovative and interesting topic, that is biochar production and its usage in agriculture. Of course, this topic, it needs very long deliberations because research is already going on in many crops, but we don't know the exact outcome for the carrying over to the field application. So, really, she has thrown some light on this topic. So, on the behalf of all the participants, we wholeheartedly thank Dr. Rinku Verma. She has taken a lot of pain in organizing this program. Thank you, madam. Thank you, for exposing us to the biochar. Yeah. Uh, Certainly, I will open the floodgates now. Now we'll take forward. Thank you. Yeah.
So thank you once again. We will just check, we go for lunch now. And please check your names because it has to be exam process. I'll just send the email to the thing. So I thank all the online participants also for having come and been a part of it. And I'm not sure if all of them are a part of it and have claimed for your certificates. So please do contact me so that you can also get your certificates and with your right names. If you have done it, then well and good. So we'll stop here and we are breaking for lunch. You all can join for lunch at the Farmers Training IFT, followed by coming to the field to see the pyrolytic unit running. Thank you, one and all. You can speak if you are able to speak. We have allowed, you can mute and you can speak, the participants. As all of you, please come for photo. Thank you, everybody. Thank you. Yes. Yeah, that has to remain, sir. Others will not get the petrol. We will not get petrol. Yes. You are very. Yes, sir. Yeah.